and thank you so much for coming this morning. This is going to be a treat. It's a little bit different than what we normally do here. We've managed to bring together electric machine motor developers as well as organizations that are leading the way in demonstrating regional hybrid electric aircraft technology through demonstrators. So the first part of this session, first 45 minutes, 50 minutes will be two technical presentations, one by Honeywell and one by RTX. And then we will transition to a panel format where organizations that are leading the way with the hybrid electric regional demonstrations are going to share their lessons learned. So bear with me, and I would like to start our presentation this morning with Jan Ludvik. Jan has a master's degree in applied mechanics from the University of West Bohemia and has a PhD from the corporate doctoral program between Max Planck Institute for Plasma Physics and the University of West Bohemia. Jan started his career by joining TRW Automotive as a test team leader in 2003. Later, he became the test and validation manager and finally engineering manager. After joining Honeywell Aerospace in 2014, he worked as technical manager responsible for the combined avionics and mechanical R&D team in Prague. In 2017, he assumed staff scientist role before transitioning to senior R&D manager, leading the mechanical department of advanced technology. Since 2022, as engineering director, Jan is leading the Honeywell's Advanced Technology Europe organization, the group of 150 engineers and scientists responsible for technology development of aerospace technologies in Europe. Jan?
Good morning, ladies and gentlemen, and thank you for my introduction, Robbie. So let's have a look on fuel cell powertrain. And I'll structure my presentation in two blocks. First, I'll start with the general talk about the fuel cell powertrains, and then I'll zoom on the Clean Aviation Newborn project, one of many introduced yesterday by Axel Krein, and that will conclude my presentation. First, starting with Honeywell, what we do on this decarbonization sustainability journey. So I'm responsible for the work in aerospace technologies. Aerospace is the largest part of Honeywell, but we do decarbonization, innovations, and other technology work in building automation, in the energy sector, in industrial automation, and in the connected enterprise. Now, zooming in on the sustainable solutions we work on, being a broad-ranging conglomerate, Honeywell addresses the sustainability on the fuel side, so biofuels, enabling wider range of the feedstocks, developing the technologies for production of green hydrogen, but as well electrification, energy audits, energy benchmarking and monitoring, etc. Now let's move on a roadmap view, and I realize you might have seen this roadmap or several roadmap once or 10 times or 100 times already, but here's my specific pitch. One of the wedges that make the difference between the daunting scenario of raising contribution of aviation sector to carbon emissions and the net zero, one of those wedges is the hydrogen technology that is a subject of competition. Fuel cell powertrains are not the only one solution for using this new fuel to decarbonize aerospace. We will compete with turboprops burning hydrogen, with turbofans burning hydrogen, and it's not one size fits all. It's not one universal silver bullet that will make the job. So let's zoom a little bit more on the segment view. So aviation is incredibly diverse industry.
with all sorts of flying vehicles carrying people and cargo. And this is my version of the crystal ball view, and just the future will tell. But what we think at Honeywell, that the fuel cell powertrains are really the mid-size, mid-range solution. So the long-range air transportation, carrying people and cargo over the continents, that's a soft playground. And hydrogen may have limited or no role in that. On the bottom side, the UAVs, the urban air mobility vehicles, they are carbon-free already now using the electric batteries, if they are fed with proper green power. In between, that's a segment for competition for fuel cells with the other solutions that decarbonize. And perhaps the solutions like propulsion for long-range business jet, that's something where the fuel cells won't work. But for the rest, for the regional aircraft up to, say, 100 passengers, that's where the fuel cell can well play. Let's move on and zoom a little bit on a comparison of the fuel cell powertrain with its next best alternative. And I've chosen deliberately the 1 megawatt power class. That's something what we are developing in the Newborn project I'll talk later about. And I would like to illustrate how different the fuel cell technology is to the incumbent turboprop. So if we look on the key parameters, the fuel cell lacks the power density of the turboprops, and it's a 2x, 3x, 4x difference, so long way to catch up. Luckily, we have the significant benefit of the efficiency. So the fuel cell at the system level, they can do 50+%, whereas the small turboprops, they would give you 25, 30%. You have to go to huge turbofans to get to 50%. And this difference in the power density and efficiency drives really very different optimization behavior. If you look on the chain of the efficiencies, and this is the aircraft view as soon as you took the energy on board of the aircraft, you see that the battery is hard to beat with very high efficiency, but you'll be limited with the range. If you need a longer range, then fuel cell with the overall efficiency, 44 in this source, as I mentioned, we can get to 50 easily. It has a benefit. The most sustainable fuel is the fuel you don't burn or consume. So that's the advantage of fuel cell. I'll later elaborate on. What comes as a complication for introduction of hydrogen fuel cells is the different nature of the fuel. Hydrogen comes with a weight benefit, approximately 3-to-1 benefit for the quantity of energy, but it comes with the penalty of the volume. And the traditional aircraft don't have the extra volume we could put the hydrogen to. So as you can see, the liquid hydrogen fuel cell powertrains, they come with fundamentally different optimization behavior and boundaries. Perhaps the extreme case is on the bottom right, showing how it would look like if we fuel the intercontinental business jet with liquid hydrogen. Even the whole volume of the aircraft would not be sufficient for storing all the liquid hydrogen. Let's move on. As in every competition, there are strengths and weaknesses of the particular contenders, the propulsion technologies. I'll briefly address some of the advantages and disadvantages of fuel cells and what we have to do. So the fuel cells come with the emission benefit. You have no particle matter, no NOx. The noise is significantly lower. It comes with the better efficiency. So this is an opportunity to push the envelope of the regional turboprop type of aircraft, which are not very popular these days. In my company, in the travel system we use, you can even check the box to avoid propeller plane. So unattractive is this way of transportation perceived. And the electric propulsion, the electric drive comes with much better noise signature and much better perception by the public. On the downside of the weaknesses of the fuel cells, the weight I've mentioned, and we need new types of aircraft that are not so sensitive to weight. We need the improved L/D ratio. The fuel cells as well lack the high altitude performance, which can be mitigated by flying lower and potentially slower. The weight, one of the solutions being studied are load-carrying hydrogen tanks so that we reduce the weight penalty. And thermal management with fuel cells, you don't just dump the heat out of the tailpipe as with the turbine, you have to remove it actively. And we are studying novel heat transfer technologies like microtube heat exchangers to mitigate that. So it's a fundamentally new propulsion technology with a lot of changes that need to happen because we are catching up on 7 decades of the turbine era, and it requires many innovation loops to catch up. Let's move on how the fuel cell powertrains could enter the aerospace or are actually entering. So the fastest way is the conversion. So there has been projects like the picture from Universal Hydrogen. We take the existing aircraft, replace the engine with an electric one, put the fuel cell somewhere, put the liquid hydrogen or compressed hydrogen tank somewhere, and quote unquote, we fly. Now, that's tricky from the perspective that we consume space that could carry people or cargo and bring revenue. And as well, we would be investing into an airframe that has its life already consumed and has been paid for already. So a bit longer term approach are upgrades. Again, re-engineering the plane, stretching the fuselage to make the space for the voluminous liquid hydrogen tanks. Stretching is known discipline. We've been stretching airframes for ages. So this is not eating into the revenue potential from the airline, but still it misses many opportunities that can be addressed with the last and the most attractive entry point being the clean sheet designs, where you have the best freedom to address the weaknesses of fuel cells. You can design the airframe to have enough volume for the liquid hydrogen tanks, bring in better aerodynamics so that you overcome the weight penalty of the fuel cell, and you come with the best optimal solution. So those was the general introduction for the fuel cells. Now let's zoom in on the Newborn project. Newborn stands for Next Generation High Power Fuel Cells for Airborne Application. This is Clean Aviation project that is led by Honeywell, executed by a broad consortium, kindly supported by the Clean Aviation and on the UK side with the UKRI. And it's not just about the financial support, it's about bringing the team together and bringing the partners with different expertise in different disciplines to work on something as complex as a fuel cell powertrain. So the consortium is building the powertrain. If I start from the tank coming from Achituri, the hydrogen is then conditioned and supplied by a system coming again from Achituri and Tesfuchs. On the air side, Honeywell is providing the air supply and treatment system, both feeding the stack coming from PowerCell from Sweden. Honeywell, with reaction engines from the UK, is addressing the thermal management challenge of the fuel cell. And then when you get the electrons out, there is the DC-DC and power distribution coming from Fraunhofer. The fuel cell power is augmented by a battery coming from Pipistrel. And the University of Nottingham is addressing the propulsion piece, developing the inverters and the EPU. So that's the consortium. At high level, it's in total 13 partners that work on 28 technologies. The project started on the beginning of 23, will run until 26. We will demonstrate the full powertrain from the tank to the propeller on the technology that is scalable from 250 kilowatts up to 3+ megawatt. This will be TRL4. We want to get this on the market, of course, as soon as possible to make the impact. We see the CS23 segment coming first before CS25 kicks in, where the emission needs to be addressed mainly. Overall, we target the 1.2 kilowatt per kilogram power density, which will be enabled by the technologies like high gravimetric index tank, higher temperature, PEM fuel cell stack with 5+ kilowatts per kilogram on the stack level, low delta P radiator reducing the aircraft drag, the cryogenic actuators for the LH2 fuel system, and high power density DC-DC converters and other power electronics element. So these are the guts of the newborn project. Now let's briefly look on the architecture, and I could spend an hour here and I'll spare you that time. So just notionally, on the air side, we have a two-stage compression, so centrifugal compressors with energy recovery. On the hydrogen side, you see the LH2 tank, two-stage evaporation preheating, feeding the fuel cell stack. On the thermal management, we have the RAN duct with the heat exchange, the microtube heat exchanger sitting in it, removing the heat from the stack and from other elements. And then on the electrical side, we have the HVDC bus with the DC-DC converters, the hybrid battery, inverter and motor driving a propeller through a gearbox. So that's the system architecture, if you will, of the newborn demonstrator. And now getting towards the end, what comes next? So as part of the newborn project, we will do the integration of the powertrain, TRL4, demonstrate it, run on the ground, job done. That's not enough. We definitely target TRL6, and clean aviation phase 2 is the ideal pathway to get it to TRL6 flight test. Early deployment will be critical for the rapid evolution of the fuel cell that is needed to quickly catch up the gaps we have against the other more established propulsion technologies. We believe that the CS23 and advanced air mobility segments are, although not being carriers of the emissions and contributors to the carbon emissions, but they have the fast innovation cycle and a lot of competition. And we believe that this pace of innovation would help to optimize the technology so that it's ready for the deployment in the CS25 segment, where it's critical, where the decarbonization impact is required. So that's the future. I hope I'll enjoy this technology coming into service and flying on fuel cell powered aircraft one day. And thank you very much for your attention. Yes, please.
Thank you for the presentation, really good. This is Yannick Fernandez from Clean Aviation. I'm pleased to see some of the mock-ups. Actually, for those that are interested, we have a 3D printed version of one of the mock-ups here for the project Newborn. And my question is around this SWOT analysis where you were showing some of the threats, particularly on weight and on drag. Do you think that when accounted this into the efficiency of the full powertrain, fuel cells will still be able to compete with more traditional combustion solutions?
Yeah, definitely. It's a function of the segment of the aircraft and the mission. But we have been running trade studies and MBSC simulations from the very beginning, and we would not have done this if the data wouldn't be convincing. Any other question, folks? Like, no. Thank you.
So our next presenter is Dr. Ray Foley. He is a Director of Advanced Systems and Demonstrations at Collins Aerospace, Applied Research and Technology. ART has the mission to accelerate transformative technologies for a safer and more connected and sustainable world. In his role, Ray is responsible for progressing advanced systems design and integration capabilities, including development of processes, methods, and demonstrations to enable scaling and transition to the business units of Collins Aerospace. He is also the site lead for the Collins Aerospace operation in Cork, Ireland. Ray is an alumnus of University College Cork, where following his PhD doctorate, he worked as a lecturer in the electrical engineering department and undertook research on high-density power electronics. He is the author, co-author of over 30 conference and journal publications. He is a participant in several national and EU-funded projects and is a board member of the EU Clean Aviation and CESAR joint undertaking programs. With no further ado, Ray?
Okay, thanks, Gaudi. So good morning, everyone. Delighted to be here in Florence. I saw some of the sites last night. It's a very short trip for me, unfortunately, but very nice place to have this discussion today about the clean aviation high voltage network and demonstration. And what I'm going to do in this presentation is talk particularly, like my colleague here, Jan, talked about the Newborn project. I'm going to talk about a project called Hecate, which is leading the high voltage electrical distribution architecture for regional aircraft in clean aviation. Just a little bit, because I don't actually spend much time talking about where I come from in terms of Collins Aerospace. I know Gaudi had a very nice introduction, but just a little bit about Collins and RTX. Collins Aerospace is a large system supplier for the global aerospace industry. We have around 80,000 employees globally. About 14,000 of those are actually here in Europe. As mentioned, we're a keen participant in programs like Clean Aviation, CESAR, and our Applied Research and Technology organization, where I work, is really at the core of organizing our collaborations within those kind of programs. You'll hear a little bit later on from my colleague Jean Thomassin, who's from Pratt & Whitney, Canada. He'll talk maybe a little bit more about the overall RTX company and how we all fit together as a happy family. So, without further ado, let me start talking about Hecate. Now, I don't know how I press play here, is the only problem.
Hecate, hybrid electric regional aircraft distribution technologies. To tackle the climate change and global warming challenge, the European Union set ambitious emission reduction targets. Their achievement, in combination with the projected growth in aircraft market demand, requires the aviation industry to shift towards electric and hybrid electric technologies for aircraft propulsion systems. This creates the need for high-power electrical architectures. Hecate aims to deliver transformative technologies considering high-voltage distribution for the electrical distribution of hybrid electric regional aircraft. Hecate develops critical technologies for high-power, high-voltage and certifiable electrical distribution architectures capable of enabling hybrid electric propulsion for regional platforms. Hecate applies a holistic approach, maturing different technology enablers in hybrid electric propulsion towards industrially relevant environment for regional platforms. The Hecate project methodology is based on the following elements: definition of the electrical distribution architecture and specifications, Development and maturation of transformative technologies in the electrical distribution, supported by transversal activities such as digital twins and electromagnetic compatibility. Demonstration and integration at a European integration ground test bench, known as Copperbird. Road mapping, impact and scalability to future platforms based on acquired know-how and life cycle assessment. HECATE's ultimate goal is the readiness of the technologies towards clean aviation phase 2 and commercial exploitation. The project consortium unites over 36 months the expertise of 37 partners in electric, electronics and control systems. Spread across 11 countries, HECATE bands together academia, research institutions, SMEs and large industrial groups under one common goal. HECATE would not be possible without a constellation of interrelated clean aviation projects and EASA support for approach to certification. This project is co-funded by the European Union and UKRI. Follow us on www.hecate-project.eu and Clean Aviation LinkedIn page.
Okay, so my job is done. What I'll do a little bit though is talk a little bit more about the whole consortium and how we're constructed, who's doing what, and then talk a bit more detail about the demonstration approach and some of the architecture that we're looking at here. So a large project, as mentioned, it's about 70 million of total effort in euros with 37 partners. So a complex project, but it's a complex undertaking to deliver both the certification pathway for this new technology, to risk reduce the technology bricks, to define the architecture and to make sure that architecture is going to be one that can achieve the target size, weight, power and cost required for this particular application. So the partnership, some of the key partners here, Collins Aerospace and Safran are really leading two elements of this. Collins really focused on the low voltage distribution, Safran on the higher voltage distribution network, working with Leonardo Aircraft as an airframer and also Airbus to really understand the requirement set for this aircraft class. And then a whole range of partners from research providing organizations to academia to small and medium enterprises. So it's really a collective that is not just working together for this project, but also driving the future industry potential, risk reducing across multiple different technology pieces. So what are those technology pieces? I mean, there's physics modeling. How do we understand what is the fundamentals around things like arc faults and so forth? Materials manufacturing, being prepared and ready to actually manufacture these technologies at the end of the project. Thermomechanical modeling, design, validation, verification, multidisciplinary design optimization and model-based systems engineering, how to actually construct and optimize these systems in the right way. Even into computer science, where we're talking about some of the aspects around the controls and so forth, testing and certification, and of course, life cycle assessment. That's cradle to grave life cycle assessment to know, is this technology really going to have an environmental impact? Perhaps we get size, weight, power, and cost down, but then if this is something that's not going to be environmentally impactful over its lifetime, then we need to take that into account as well. Partnerships, there are people from our companies and partners from all over Europe, particularly in France, Germany, and the UK, but across many other EU and non-EU member states as well. And a good proportion of SMEs and also RTOs and universities within the project as well, which is, I think, very important to drive that future generation of technologists, to also create a whole constellation of small companies who can participate within this industry as well. Talking about some of the aims and objectives. So in terms of aims, we want to create a high power, high voltage certifiable electrical distribution architecture for the regional type aircraft. Develop those technology bricks and enablers at TRL 5, particularly for regional platforms, but also these bricks could have potential applications and uses in others like UAM, short, medium range, etc. So that's potentially a future for the outcomes of this project. Also look at things like the issues of high voltage in low atmospheric pressure, EMI, all those kind of things that we need to take into account. And looking at things like digital twins to enable us to be both ready for the sort of introduction into service and the NPI piece of this, as well as using these products in service, how we do like monitoring and so forth, using those digital twins. So that's an important aspect as well. And of course, overall contributing to the reduction of aircraft greenhouse gas emissions, aligned to the sort of 30% greenhouse gas emission reduction targets by 2035 and zero emissions by 2050. The project has 6 kind of then objectives, and various different partners are contributing to those objectives. The first being development of that holistically optimized electrical architecture. So the optimization is important, and also the various elements that build that up. The technology brick development to TRL5, and I'll show a little bit about the timing of those in a later slide. Mitigation of the high voltage and EMI phenomena, development of those digital twins, and the certification pathway. So we're working with the EASA on, how are we going to certify this this architecture, and it's a very good partnership in order to prepare us as a consortium, but also to help prepare EASA for the certification eventually for these technologies. And then we also work on a roadmap for what's next. What's next could be a new hybrid electric regional aircraft. It could also be the incorporation of these technologies into perhaps a short, medium range aircraft, etc. In terms of how we've structured the project, we have a definition of the requirements phase, and we're working, of course, with the airframers on that, so Leonardo and Airbus in particular. Then development and maturation of those various different technologies, and also the transversal activities like EMI, digital twins, and so forth. So that's work that Saint-Exupéry, Airbus, Collins, Safran are really kind of driving that whole technology bricks and transversal activities part. In terms of demonstration and integration, we're working with Safran, particularly on the Copperbird integration. So that's where all this will come together, and you'll see a mock-up of that demo in a future slide. And then the road mapping and the life cycle assessment part, which Airbus and Leonardo are driving in the project. I won't go into this in so much detail. I guess we've talked a little bit already, but really I talked about the primary distribution really being the Safran activity, the secondary distribution being Collins-led, also with the power conversion at Collins, and then Safran working on the power management and control systems. And then all of these different work packages, 2, 3, 4, and 5, are what we're bringing together in our demonstration. In terms of impact, and this is kind of how we're assessing our performance as a project, right? There are different ways of assessing that. I guess there's an industrial competitiveness aspect, and of course there are industrial companies involved in this program. So, aspects of that which are going to drive the economy and the potential economic outcome. There's also the environmental and social side, right? There is, of course, the sustainability objective of the project, but there's also things that we get into, for example, like training of the next generation of engineers, jobs, and so forth. And then there's, how do we link with the EU and public policies? That can be around the impact and certification, or fostering cross-sector collaboration as well. So on the technical approach, here you can see basically a simplified electrical architecture for the system. So this kind of gives the boundaries of what we're working on. There's a KHV-DC network, now not quite kilo, it's about 800 volts. So that's kind of where that network is connected to the batteries, fuel cells, through DC to DC converters, and also connected to the sort of propulsion side on the aircraft, assuming an electrical propulsion. As you step down, you get to a high voltage DC network, 540 volts DC, also with outputs to 115 volts AC, or 230 volts AC, I should say. And then one level below, where we have the sort of lime green, which is on the low voltage network, which is a 28 volt DC to DC network. In terms of maturity, we started the project assuming, or at least with a high level of confidence, that the technology we were starting with are at TRL3. And that's across primary, secondary distribution, the conversion, power management, etc. We're in a phase right now in 2024 where we're working on the TRL4 progression reviews and so forth. And the technology integration and all the bricks will be at TRL5 by the time we get to the end of the project. The LCA approach, I mentioned that this is cradle to grave. We have sort of a flow diagram here showing how that's integrated. Obviously, there are requirements that come from the sort of aircraft demonstrator at the top there. So you can see HERA is providing some of the top-level aircraft requirements, the level of hybridization and power consumption and so forth on the aircraft, and also the aircraft lifetime and utilization. From our point of view, creating these technology bricks from Hecate, we have sort of an electric propulsion level, where we're looking at the system level life cycle analysis at that point, and also the subsystem life cycle analysis. And then we have various different outputs, KPIs, and the environmental impact that we're looking at there. Currently, we're around cradle to gate in terms of looking at the technology development, the technology bricks, and we will, in the future, be completing that assessment to get the full life cycle. This is really just a look at the demonstrator. So this is kind of a more detailed view of the architecture I showed earlier. So you can see the various different bricks and how we're approaching this. One key element is that we're going to simulate some of this, so kind of have a real and simulated interactive demonstration so that we can simulate faults and so forth. So the area outlined in the red hash line is going to be simulated as part of our demonstration program. The various different elements, like the KHVDC, will be tested at 250 kilowatts. The converter down to the next level, high voltage, will be tested at about 100 to 150 kilowatts. And the AC and low voltage DC loads will be tested between 20 and 40 kilowatts as well. We also need to test functions, does this all work together? What do the protections, how do the protections work, and how does the monitoring piece work as well? So that's all part of the test plan for the demonstration. So finally, this is what the test rig will look like in sometime between the middle and the end of next year. This is at the Saffron facilities at the copperboard we talked about. There's a trolley with all of these elements integrated. You can see the kind of mock-up on the right-hand side and maybe an early stage on the left. We'll start the preliminary integration in a couple of months and the full integration by the end of next year. So, what have we done to date? We've got the top-level aircraft requirements. We've been aligned with the HERA program within Clean Aviation, which is the Hybrid Electric Regional Aircraft Demonstrator program. We've been designing and developing technology bricks so far. We have started our impact monitoring process in terms of the life cycle assessment, TRL process, etc. We've developed a V&V strategy and test plan for the program. All the preliminary design reviews have been completed. We've also been cooperating, collaborating with the various other clean aviation programs to make sure the requirements, etc., link. Next, we'll work on the critical design reviews for the primary and secondary distribution technology bricks, and then also make sure that these are continually aligned with the HERA, but also as the orientation of Clean Aviation Phase 2 is emerging, what those bricks need to deliver. And we'll also work on the preliminary model for the digital twin of the architecture. So that's it. I hope you got a good insight into the Hecate project. I'm happy to take any questions. If you have very detailed questions, I would particularly refer you to the coordinator, Nacho Castro at Collins Aerospace, or also Jerome Valère at Safran. So thank you for your attention. The previous slide. Oh. You guys need to be quicker on the cameras, no? Sure.
Good morning, Ray, and thank you for this very nice presentation. Sébastien Dubois, Clean Aviation. I have a couple of questions. First of all, I would like to understand what is, in your view, the voltage envisaged for the next electrical network for the future aircraft generation. This is my first question. My second question is about what kind of commonalities can we expect for regional or SMR kind of application, and what are the main differences in your views? And the last question, how do you expect to certify or at least to accelerate the certification aspects for potential introduction of such technologies?
Sure. So first was voltage levels. I mean, here we're working with, well, let's go back to an architecture here. So it was 800 volts at the sort of propulsion level, 540 volts at the DC level, also 230 volts AC, right? Potentially if there's legacy requirements there, and 28 volts at the low voltage DC. Your second question was around
commonalities between SMR and HE.
Yeah, I mean, we've talked a little bit about this. I mean, I think the levels we talk about, there's no particular incompatibility. There may be more or less of some or other. Depending on how, let's say, risk, or maybe risk is not the right word, but depending on how adventurous some of the airframers want to be, there may be more or less of some of these architectures. The distribution, for example, on a short medium range might be AC, potentially. 230 volts for the low voltage, or for the aircraft level distribution. So some work to do there, but I think the levels are somehow converging at that right way. From the certification point of view, you know, I said earlier, I'm not sure if you were here at the time, but you know, we need to be prepared in terms of, you know, developing a path to certification, but EASA also needs to work together with us to understand what are the risks and the things that they need to be cognizant of. So, like, it's a collaborative approach, and I think this project is very good in that it brings, you know, there's 37 partners here, many of those who will be either developing or producing these kinds of systems in the future. So, I think we can all work together to do that. But there's you know, there's a lot of elements that need to be addressed together. Thanks, Sebastian.
Hi, thank you for the presentation. My name is Sabri, I'm representing KLM. I maybe have a very simple question. As you mentioned, there are 37 partners working on this, and I'm wondering, in the end, if you come up with a final product or a final integratable product into an actual airframe, who's going to benefit from this? Who's going to run away with the prize? Like,
society,
what can we, right? Have you thought about this?
No, but it is really... you know, the way these projects are structured, each partner will, you know, develop their own intellectual property and so forth. So I think it creates an industrial, potential industrial collaboration, supply chain, and so forth, right? I would expect that the elements that are coming from universities could be licensed and so forth by the various different industrial players. So, you know, that's part of the benefit of these European programs. They create the context for development of technologies that maybe a company on their own would find a little bit too risky, either because they don't have the partnership or because they don't have the investment. So I think that is one of the key benefits of the public-private partnership of clean aviation.
Okay, thank you.
Good morning, Trevor Young, University of Limerick. Nice presentation, Ray, thank you. My question comes to something that you've spoken about a few times, and it also was brought up by Sebastian a few minutes ago about certification. Now, I'm aware that EASA have put forward a framework of certification readiness level, which is not quite comparable with the technology readiness levels and the maturity gates that you've actually indicated there. Have you had any detailed conversations with EASA as to how you might align your gates, your preparedness with their expectation and the way they've actually expressed their certification readiness levels?
Thanks, Trevor. So we're part of the Concerto project, which is developing those CRLs, I guess, certification readiness levels. The team are in a lot of contact both with the Concerto project and EASA. So I don't have a specific like CRL level that for this project, and maybe we can follow up on that, on the specifics, what that is and what it looks like. But certainly it's part of the plan for the project.
Yeah, it's an interesting idea that they've put forward, and has application, particularly with novel technologies such as what you're working with. There's no real novelty in some of the other areas, which for them is standard working as usual. But of the many technologies being evaluated and developed within clean aviation, this certainly is extremely novel and could well be a good candidate for exploring such an approach.
No, agreed. And with the level of new innovation and technology that's being brought forward by the program, and the sort of ambition, the skip level or skip generation ambition of the program, there's a lot of new things that need to be brought together at one time. So yeah, it's a very powerful approach, I think. Thanks, Trevor.
Hi, nice presentation. I'm Mike Walls. I work for the FAA, the other regulatory agent. In your presentation, a lot of the data that you guys are going to supply, is that going to be available to a lot of the standards organizations? Because that seems to be one of the things that's holding us up a little bit. So are you guys going to supply them with some data, and not just ERIKA, SAE, ASTM, and all the other organizations as well?
So at the moment, I don't know if there's a formal approach, honestly, and I could find that out for you. It does sound like it makes sense, right? There are parts of each of the partners, including Collins, have members on those various different committees, right? So I'm not sure if, as I said, there's a formal approach in the project, and I'll work that out. But certainly, individually, each of the partners are playing their part to participate in those standardization agencies.
Okay, and the other part is going from your bottom up. Right now, aircraft, we're pretty straight up to about 540, 270 DC and everything else. It's the isolation of all the propulsion networks or the higher voltage networks that's the issue. Are you guys going to be a proponent of actually monitoring the isolation between the buses?
Yes, I mean there's a whole element of like well, you can see the architecture here. That whole gap between certainly the 800 volt 540 and down. There's a lot of work going on in the design of those power converters for that. So it's not like we just do a simple power conversion. It's designed with all the full level of requirements for isolation, etc. Involved.
Understanding that part, but the other part that goes with that is when you go through the failure mechanisms and you look at the actual protection that you're using, any one of those failures can actually affect the protection in the other bus. Yep. And you did mention arcing and all that. In the floating buses, it's very different than what it is on the others. So are you guys going to go into those aspects as well?
Yes, to my understanding. Again, I'm not leading this project directly, so I think it's probably a more technical question. Okay. But certainly we can have a chat afterwards, and I'll connect you with the team if you want to follow up. So.
Right. Great, thank you.
Thanks, Mike. Okay, thank you all.
Okay, so the format for the rest of the session till 12:30 is going to change a little bit. What you're going to be hearing is these are the innovators, leaders that are actually doing practical vehicle level integration and tests of their electric powertrain systems. And what I've asked each of the presenters to do is to provide like a really high-level overview and touch upon some key lessons learned that they would like to share with us as the community. And then they're just going to sit at the table, and we'll just have a pretty much open Q&A session, asking questions, whether they're from each other or from you, the audience. So to start this off, I would like to invite David SERCOMBE. He is from magniX. David has been a part of magniX's story since its inception. His background is in electrical machine design, and he holds multiple patents in electrical engines for aviation, as well as conventional and superconducting electric machines. He previously led the development of the Magni core engine technology as chief design engineer and chief engineer. He is currently serving as the magniX Vice President of Engineering, leading the charge to develop and certify magniX electric powertrain. David.
Wow, good morning, everybody. Thank you very much. Thank you, Gaudi. I've got a little bit of a unique role this morning in that, coming from a motor background and some of the more technical presentations earlier, and then the lessons learned going through because a lot of our engines have been on different flight demonstrators. So a little bit being the Ponte Vecchio for the session this morning. So bear with me. So fundamentally, I don't know if everybody's heard of MagniX, but we're developing electric powertrain solutions for aerospace and beyond, but here we're mostly talking about aerospace. And we're really getting a chance to talk about some of the motor technology to start off with, and then the lessons we've learned integrating that motor technology with our partners onto different flying platforms. We're in a pretty unique position of having both developed the propulsion system in-house and flown in 5 very different flight demonstrators over the past 5 years. So, I was reading this morning, I think it was a quote by Maslow that basically says, when you're a hammer, everything looks like a nail. So, as a motor designer, when I think about flight demonstrators, it looks a little bit like this. So this is sort of our story in engines over time with the flight demonstrators they've been used on and the Iron Bird at the start. So starting off, 2017, the Magni 5 kilowatts per kilogram, power dense, direct drive. You can see it there mounted on the front end of a Cessna Caravan Iron Bird that we had built up in our test facilities at that particular point in time, driving a 206 prop. So from there, it was really taking the conversations we were having at the time with potential partners on what they were really looking for from a propulsion system, and some of the lessons learned from our original integration, and that led to the development of the Magni 500 and the 250 family together. And so really, it incorporated our motor technology. We were developing a motor controller at the same time, and called the Magni Drive, and it was optimized for direct drive operation in the 1900 RPM to 2300 RPM range. And that's really critical, looking at where the market was going, at least for these smaller aircraft, and what the power range was going to be reasonable. But then, more importantly, thinking, at least in these early stages as well, where did it sit in the context of integrating into the aircraft? So one key aspect of the technology right from the get-go was the ability to interact with conventional propeller governors, right? Being able to drive a propeller, take propeller loads, do all of the things that an aircraft engine should be able to do. The Magni 500 engine ended up being used in the eBeaver and eCaravan flight demonstrators, and we'll talk a little bit more about those in a little bit of time. But that was in 2019. Now, its smaller sibling, the Magni 250, again, sort of a very modular design, ended up finding an interesting little niche in a demonstrator, and a rotorcraft demonstrator. So it was quite an interesting conversation with a company that was looking to do that. Certainly an interesting way of entering the eVTOL world, in a sense, right, with the original VTOL. And so we worked quite extensively to integrate Magni 250 into a full electric Robinson R44 demonstrator, just sort of some interesting challenges along the way, and we get to lessons learned piece of the puzzle. Lessons learned piece of the puzzle, right? So from there, and sort of the next step was really to take everything that we'd learned from installing things on aircraft, right? From testing, from the Iron Bird testing, put all of that into, well, okay, do we keep going along the path that we're on in certain areas, or do we take some of those lessons learned and fold it into the next generation? That led to the development of the Magni 650. So really the key changes with this one, and this is very interesting, right? From a internals point of view, from a motor design point of view, very little shifted from one to the next. There were little design to manufacturing improvements, et cetera, et cetera. But mostly it was around simplifying the interfaces with the aircraft, right? In the early installs, it was really motor and motor controller, and the different systems became more of the burden of the airframer. As we moved along with the 650, we're like, okay, let's simplify the mounting interface. Right, let's simplify the prop governor location, the interaction there, in anticipation of some of the more interesting elements of governor operations, such as beta and reverse, which is sort of a key part of most people who are operating these aircraft, what they're really looking for, and more tight integration of things like the oil system and the cooling, the cooling and lubrication systems of the engine itself. Right, what we'd realized was that okay, the technology brick of power density, torque density, each of those things is a great starting point. And you need that to kind of even be at the starter's gate. But the next step from that is really saying, okay, this is an engine that fits within an aircraft context, and so how does it support the systems that exist on aircraft? How does it do the things that aircraft need it to do? How does it support these legacy elements? And I think thinking like that led to that level of integration. And that was used on the AVIATION Alice, 2 of them in point of fact. A clean sheet design, and then you saw a little bit of this earlier, but it was also on the Dash 8 fuel cell hydrogen demonstrator that Universal Hydrogen did in 2023. Very interesting application as well. And so, where are we now? Where have we reached? The next iteration is the Magni 650, the V3 as we're calling it. It incorporates, again, the same kind of lessons, right? Smaller changes, smaller tweaks. But of course, we've done many hundreds of hours of dyno testing, of Ironbird testing with a prop, and the flight tests that happened. You know, they're taking each of those lessons learned. Again, coalescing the experiences and actually integrating these into flight demonstrator platforms. And then everything we've learned on the regulatory engagement piece of the puzzle, right? We've been on this journey for a very long time. magniX was one of the first companies to be issued a special condition to Part 33 that paved the means for the certification of electric aircraft, and we've been working diligently and collaboratively with the regulators on the various elements of that, right? Getting the cert plan accepted, engaging on the topics of the language in the form of white papers, having a very good dialogue back and forth on, you know, where are the gaps from a regulatory point of view, or from a means and methods of compliance point of view, and how are we going to address those, you know, through test and through other means, etc. So this is the certification candidate. It will be the engine that will be on the Harbour Air eBeaver product. So we're joined today by ERIKA HOLTZ, we're talking later on. You know, Harbour Air and magniX have worked very closely since 2019, since the first flight, which we'll talk about in a little bit. And it's that engine there is actually currently on test. After having been tested in our facilities, it's moved to the NASA NEAT facility for high altitude testing, and we'll cover a little bit more of that later on. So, the non-engine view of the flight demonstrators looks something like this. And I think this is the, you know, it all started December 11, 2019, close collaboration with Harbour Air and magniX, and we've had the first flight of a fully electric DHC-2 Beaver. At that point, it was like the largest fully electric plane. So both ERIKA and I were there for that first flight. You know, I think the amazing bookend to that story has been this past Oshkosh Air Show, where we debuted the actual product, the eBeaver plane that will be brought into service, and as at the Oshkosh Air Show, that was just a fantastic experience. So I want to really start at the beginning here, because you've got to think, you know, the mindset around electric aviation in 2018, 2019, what was possible, how is it going? And the conversation internally, well, I know the conversation from my perspective was, well, we have an opportunity to do a demonstrator. And as an engine designer, I'm like, fantastic, you know, little ground test unit over here or something along those lines. What are we doing? And it's like, well, it's going to be fully electric. I'm like, all right, 2019, okay, fully electric. It's going to be a seaplane, okay? And it's going to be in the winter in Vancouver. And, you know, you rise to the challenges is probably the way that it looks like. And there was all that question at the time, you know, why? Why take on each of those things all at once? You know, there's a little bit of mild hybridization going on and all these different things. And the answer we kept coming back to was, well, if we can tackle each of those challenges, we can probably tackle all the rest that come along with it as well. And I think that set the tone for how we work together so collaboratively. You know, and then that was followed up from that flight in eBeaver, and I'll let ERIKA talk a little bit later on about the subsequent flight testing of the eBeaver. But you know, in 2020, we followed up with the Cessna Caravan, retrofitted with the same Magni 500 system, really designed around flight testing, around extended operation. We were able to take it up to 10,000 feet at that particular point in time. Very, very interesting program. Took all of those lessons learned, folded it into the 650. You know, and then there was another sort of left field opportunity that came up in terms of integrating a 250 onto the Robinson R44. Again, it was one of those interesting conversations where we looked at the problems that we'd had to solve in order to be effective in the prop-driven world. Were not dissimilar to the challenges that were needed to be addressed in the Robinson application. Some very unique loading, some very challenging elements from a bearing point of view, all of which were, you know, sort of made us perfectly placed. And so that, in 2022, that first flew, including a point-to-point, Palm Springs to Coachella, electric aircraft, a very interesting application, very interesting opportunity. And then, again, in 2022, we had the first flight of the AVIATION Alice. So we moved from these retrofits to the AVIATION Alice, clean sheet, from the ground up, designed to take advantage of, you know, what you can do with electric aviation. 2 Magni 650s on board, 1.3 megawatts of installed power. Absolutely amazing to see that thing soar off into the distance and then return safely at the end of it all. Quite the experience. Again, just ratcheting up that element, all electric, but a clean sheet aircraft in this particular instance. And then, you know, in 2023, there was the Universal Hydrogen flew the Dash 8. One turbine had been replaced with a Magni 650. And look, you know, Unfortunately, UH2 were unable to continue with that project, but it remains the largest hydrogen fuel cell aircraft to have flown to date. And I think it's one of those instances where you look at, like, this is the same technology piece, but the application spaces are so incredibly varied and different. You know, one conversation we're going to have is about lessons learned and things like that. One of my favorite moments is we spend an awful lot of time in test. That means prop testing. That means you know, having the facilities in Everett to actually go and do that. I remember when the Universal Hydrogen propeller rocked up at our facility. And you know, you design things for a certain range. You think, well, okay, let's try and get the envelope right for each of these things. And then this propeller arrives, and it's a monster. An absolute monster. So I grabbed our head of the structures and I'm like, here, come and have a look at this. And so we've gone down the back, unboxed the propeller, and I always remember it's just sort of, I showed it to him and he's like, ooh. And so he's gone away rather quickly, and it's like, and it's come back and it's like, oh, no, we're still in the envelope, we're still fine, we've got plenty of margin, we're all good to go. So one of those interesting things about like integration, thinking ahead, you know, what's the envelope you're going after, and then seeing that the opportunities that come up, you know, from where I considered the technology was going to go, what I thought it was going to be applicable to, and how that's actually played out in real life. And it just speaks to the notion that, you know, as humans, we're sometimes very, very bad at being able to predict what the future's going to look like, and we're sometimes very bad at sort of estimating where technology is going to go. But at the same time, the act of actually bringing it to bear, you know, proving it out, has a manifest impact in terms of where these applications go and how they're being developed. And I think that sort of speaks to the very different, shall we say, you know, the very different application spaces that all using fundamentally the same technology, tweaked along the way for sure. I think each of these programs has had their lessons learned, and I have, I think, 10 minutes, so I'm just, you know, keeping it kind of compact. We could fill a book and a half, I'm sure. But at the same time, you know, I think what's important is just beyond the technology, right? And the first takeaway is really think about the integrated system. Have an integrated system. Realize that your engine, your propulsion system, your powertrain exists in context and there has to serve the various needs of that context. The second one is be an integrated team, right? You know, in the past 5 years, we've flown fixed and rotary wing aircraft. Clean sheet, retrofits, all electric, hydrogen fuel cell. Each of those came with a team that was really tightly integrated, right, between us and our partners. And that created, I think, this environment for success that, you know, allowed information to flow freely. It allowed the conversations to happen, the good ones and the hard ones. I think it created some really, really interesting stories and anecdotes about how you go and do some of this stuff, what it takes to actually get things into the air in a safe and reasonable manner. So the question is, right, after each of these demonstrators, what's next? What comes after that? And this is the vision vehicle for the EPFD project, which is the partnership between NASA and magniX, aimed at reducing barrier risks for large hybrid electric aircraft. So the vision vehicle is a 50-seat regional aircraft, 4 engines in a parallel hybrid configuration. There's some things on there. But really, I want to talk to this notion of barrier risks, right? What are we actually doing with this demonstrator in relation to all of the things we've done? We have done, you know, many flight tests, many integrations. We've learned a large number of things along the way, and we'll talk about some of the outworkings of that in my presentation and in ERIKA's to come as well. But what are we doing next? You know, and I think we're looking at the barrier risks that exist to this kind of parallel hybridization. You know, you have battery densities at scale. So this project is going to have a significant proportion of battery development, aligned with magniX's recent announcement of the Samson 300 battery cell product, battery pack product, I should say, rather. You know, it's going to look at integration. I keep saying that word over and over and over, but it's because it's really important. What are the challenges with integrating, you know, an aircraft in this kind of scale? So going up to Part 25 aircraft, we've generally been Part 23, Part 27. EMI, of course, everyone's favorite topic, and electronics at high altitude, everyone's other favorite topic, and we'll talk a little bit more about that. You're going to talk about this greater than 800-volt system parts. I learned some new nomenclature today from our good friends at Collins, the KHVDC, for greater than 800 volts. So yeah, I think I'm going to be repeating that. I think that needs something that really needs to catch on, right? That's awesome. And then fundamentally the certification element. So the EPFD demonstrator is, you know, the EPFD vision vehicle, right? One of the key barrier risks to Part 25 aircraft is still certification of the electric powertrain, certifiability of the batteries, and the other attendant issues that go along with Part 25 certification, realizing it's different to Part 23. Okay, so this is the actual demonstrator that we're planning. So it's taking a a -7, de Havilland -7. So we've done the Beaver, the -2, we've done the -8, we're doing the -7. There might be a trend. It's going to take 2 gas turbines off and eventually replace them with 2 Magni 650s in a parallel hybrid configuration at the aircraft level. It's going to include 2 450 kilowatt-hour battery packs designed by us with 800 pounds total payload, and some notion about what the minimum viable energy density at the pack level is going to be required for this demonstrator to be effective. Really, the important part of this is the 4 square over to the time. We're going to see that term barrier risks again, so looking at actual demonstration of these things in order to burn down and reduce the barrier risks both through ground testing and flight testing. This will be a very capable vehicle, something of a flying laboratory. And so it'll help us actually ring the system out in the way that says, well, this is what we've been able to do on the ground, this is how we ring it out, and then we take that up into the air. But again, focused on things like EMI, lots of systems on this aircraft, lots of legacy systems, what's really happening there. Focused on high voltage at altitude. A lot of challenges, a lot of people talking about what can and can't be done. I think we're getting to the point where we've got some very, very good demonstrations around what the challenges are and also how you address them. And more importantly, how you prove that you've addressed them, which can be its own challenge in itself. We have the down to ground and demonstration flight, technology maturation, and this really key part, the closing the regulatory gaps. So there's a big work package associated with looking at gaps, be they part 23 or part 25 and even part 23, and how does that need to evolve? Where are the gaps? But more importantly, how do we get a data set that really helps us understand what it will take to close those gaps? And that is, I think, a really important legacy element of this, is to be able to say, okay, this is predominantly a project about data, and data that leads to more information being available, which is going to close the regulatory gaps, and therefore start to chart the path through which these things are actually going to get certified, in addition to Magnex's own efforts on its type certificate for the engine under Part 23 special condition. I'm going to blitz through this really quickly. Just to give you an idea about how we're going to do it. We've done the items in the past, but little lessons learned about how we do some of this stuff. So there's a baseline flight testing that has been completed of an unmodified -7. There's really a phase 0.5, which is where they add the livery and all the colorful things. We did the rollout of the -7 just recently. It's all dolled up in its livery, so it looks really, really good. And then the first phase is going to be taking one engine off and put one EPU and one ESS in. It's an important part of the phased approach because, again, it will allow us a slightly greater envelope than the 2x2, and so a chance to go and gather a very large amount of good quality data at altitude, various operations. We're talking about hybridization, we're talking about hybridization factors, we're talking about the ability to shut down engines in flight, etc., and restart. Some really interesting and challenging corner points for this kind of technology, especially when things get, it's like it's one thing to design a power dense motor, it's another to design a power dense motor that drives a whacking great prop and operates, all over the temperature spectrum and vibration environment that you get in something like this. And then phase 2 will be replacing both engines and doing a full demonstrator. And again, baseline testing allows us to basically really compare the baseline performance of this engine, 4-engine -7, with the improvements that we're going to make as we go through phase 1 and phase 2. So it's hard data, an extensive flight campaign. It's flight testing with a purpose for sure. We completed the baseline flight test. It says winter 22 and 23, winter 2023 to 24, so that was quite exciting. I know the team had a bunch of EMI kit in there to get some baseline measurements, different flight performance and fuel burns on this engine. And then what else are we doing in the meantime? Well, I spoke about that V3 that we built easier. That's actually in the neat facility. One thing you'll notice about that engine, with all bundles of wires, is it's heavily instrumented. We have, routinely recording about 150 channels of data coming through, voltages, currents, vibration, temperatures, flows, pressures, temperatures. Anything we can basically put a sensor on, we've put a sensor on in that equipment, including a lot of rotating sensors and things along those lines. So a lot of good quality data. We finished phase 1 of the neat testing. We took the engine up to 27,500 feet in that instance. And, for those of you, because the Aeronautics Conference, actually we took it up to 27,500 feet at ISA plus 35, so a little bit higher if you actually bring that down to ISA plus 0. Really focused on some of these high voltage at altitude on the KH VDC system. looking at the things like partial discharge phenomena like that, not only how you measure it and how you determine that it is in the system or how you determine it isn't in the system, but more importantly the latter, right? How do you prove a negative? A lot of interesting work from that one, a lot of good results. The team have obviously poring over the data set. It's quite extensive. We're gearing up for phase 2 of that test facility now. Again, a fantastic test facility, fantastic collaboration with the NASA team and magniX. And it comes back to that point I was trying to make about being an integrated team, right, with each of the partnerships that we engage with to the greatest extent that we can. So, that is the end of it. So I'll finish on the next slide. But just to kind of sum up, right? My personal feeling at this particular point in time, and you see this as a bit of an inflection point in electric aviation, be it battery electric, be it hybrid fuel cell, be it hybrid, be it hydrogen fuel cell. I think that we have this opportunity, especially in this instance with the programs that are going on, to create a kind of data set that will form the basis for how these things are developed, but not only how they're developed, how they're certified, and ensuring that when this enters into service, it's of the pedigree that we all need it to be for electric aviation to be something that's really exciting and compelling for the people that are going to fly on it. We're going to do this by thinking holistically about the powertrain, right, including energy storage now, integrated with the aircraft and its systems. So not just thinking about an individual technology brick, but how does that technology brick work in context in a product? We're going to encourage a tight level of integration between magniX and our partners, such as Harbour Air, such as NASA, such as the people we've worked with in this instance, because that really is where the magic happens, right? When you get teams working in that sort of synergistic manner. And the most important thing, I think, number 3, is, being one thing we learned from flight testing, from demos, from each of these things, is how to be intentional with the testing campaigns, right? Particularly in the fairly extensive campaign that will be a part of EPFD. This test asset with EPFD is going to allow us to develop a data set that's going to reduce the barrier risks facing electric aviation, especially in Part 25 aircraft and below, right? And thereby helping to address gaps in the current regulations and amongst the standards committee. Ultimately, this is going to support a robust path to certification of the engine and the powertrain, and it's going to facilitate, entry into service, right? You can't enter into service until you've got a certified product, and I think that's the bit that sometimes gets lost in the weeds sometimes. So, thank you very much, Gary.
Now we're going to hear from our partner, Pratt & Whitney Canada. Jean Thomassin was appointed the Senior Director in New Product and Service Introduction at NPS at Pratt & Whitney Canada in 2020. In his, Jean. In his role, Jean oversees the company's efforts to develop enterprise-level requirements for future sustainable propulsion technologies, systems, and business models. Jean assumed his role acquiring more than 20 years of experience working for Pratt & Whitney Canada, United Technologies Corporation's Chief Technology Office. More specifically, he joined the CTO after serving for 2 years as Senior Director, Systems Engineering at Pratt & Whitney Canada. Recently, he is the Project Director for the Pratt & Whitney HEP Demonstrator Project, a joint collaboration between Pratt & Whitney and Collins to develop a hybrid electric propulsion technology demonstrator. In addition to these responsibilities, Jean played a significant role in the development of innovative technologies. He has a bachelor's in electrical engineering from the University of Sherbrooke, a master's degree in mechanical engineering from Concordia University, and a PhD in mechanical engineering from the University of Montreal. Jean.
Thank you for having me. So before I dive into the lessons learned of our flight demonstrator, I will be touching a bit on the context. So I am part of Pratt & Whitney. Pratt & Whitney is also part of a bigger corporation called RTX. So RTX is the legacy Raytheon handling military equipment. Collins Aerospace, my colleague Ray is from there, so it's basically, it's amazing, Collins. It's like, they do everything except the tube, the wing, and the engine, but everything else they do, so it's pretty amazing to have them as friends. And then Pratt & Whitney. So Pratt & Whitney is divided in 3 divisions. One for commercial engines, one for military engines, and us for the small engines, call them small engines. So we're dealing with airplanes less than 100 passengers, but also with helicopters, general aviation, and business aviation. So we've seen that chart many, many times over and over again, but let me give you my spin. So the way I see the y-axis there, to me, is the energy consumption. So energy now comes like the hydrogen is attached to carbon. That's what we know. But fundamentally, what we need to do, and it's funny because I would be from any other industry working on mining systems for cryptocurrency. I would show a chart similar to that. We are very hungry for energy consumption in our society. So every industry needs to do its share of it. So we are part of the transport industry, and my role and what I'm after and what I can control is to minimize the energy consumption per seat mile. Then my system has to be agnostic, for whether the hydrogen is alone or attached to carbon or nitrogen or wherever, the system has to be agnostic to it. But fundamentally, we have got to minimize the energy consumption per seat mile. And this is what this demonstrator is about. So Pratt & Whitney, basically, we've been improving efficiency of the thermal engines forever, and we will keep doing it for another long time going forward. The engines today, you don't even need to talk to us. You use your book, you select the right amount of sustainable aviation fuel, you can blend it up to 50%, engine is perfectly fine with it. So the challenge on sustainable aviation fuel, and their most recent engine, they can work with 100% of it. So the challenge, like we heard yesterday, is more in the feedstock and getting the volumes to aviation. But all in all, our engines are pretty much agnostic, and they can use the sustainable aviation fuels. Hybrid electric, we're looking at it in a way not to replace again the fuel really, or the heat engine really, but we're looking at using the electrification to improve the cycle. So power electronics, electrical machinery, they're very good for power, not so good for energy because of the energy source, right? So part of what we're doing is, again, we're using electricity and electrical power augmentation to improve the engine cycle. Hydrogen is interesting too. I mean, if you're going to switch to hydrogen as the source of energy, pure hydrogen, may as well, now the gas stream is rich with water content, so you could do a lot. You want a very high efficiency system there. But also, I think, this is my personal opinion, I think that you should have like a dual fuel solution. So you could do a small missions with hydrogen to handle it. And all the safety stuff, alternate stuff could be done with liquid fuel. I think could be a valuable solution, but it will increase the complexity of the systems. But all in all, the fundamental here is we want to strive to use less energy and be agnostic to the energy source. So we are looking at thermal efficiency, the heat engine, propulsive efficiency. The GTF is a good example of that. Hybrid electric propulsion, again, I want to use electrification to help my engine cycle and my vehicle efficiency, really. Sustainable aviation fuel, again, the engines are agnostic to it. We're looking at hydrogen. We think it is very important. But we'll see where the world goes in terms of energy. And of course, our business is to be green, and we're trying to minimize our carbon footprint across our facilities. So I'm getting into the demonstrator. So we're looking at the different size. I would say in the smaller size, we're looking at introducing new capabilities with electric. They all use about the same amount of electrical power, but the small one is a higher fraction of electric versus mechanical. In our demonstrator, it's a parallel hybrid electric propulsion system. We're shooting for 30% improvement in fuel efficiency. But we're also opening a design space for new airplane design that is very interesting. So we aim at keeping or improving the productivity of the airplane. So airplane is there to fly fast and carry many people over a decent range. So we don't want to compromise that. And we are using the same electrical equipment to the larger airplane systems, like the single aisle. And again, it's a lower fraction of power, but can improve overall the cycle. So diving into the demonstrator. So we started that a few years ago. We were well supported by the governments in Canada and the Quebec government. So it's a Dash 8 airplane. We are replacing one engine by the hybrid electric power plant, and we carry the battery. In that case, we're using a 50-50 split. I think 50-50 split could be better for a CS-23. But it's not very important for this demonstration because what we want is to have all the technology blocks to architect the airplane of the future. So there's a lithium-ion battery in there. There is also a high voltage distribution system. We're running the system at a max voltage of 1200 volts in that case here. And there's also innovation in the heat engine. So we reached the PDR at the airplane level end of last year. Very happy with that. We kept going through 2024 to de-risk the engine. We had some exotic materials in the core that were a bit of a challenge, so we demonstrated that. So we went to the full power parallel system on July 21st, just before the Farnborough Air Show. We're super happy with that. The power was in the box and the efficiency was in the box too, and there's room to improve, so we're super happy with that. So we're steaming forward now to go and install it on the airplane. In terms of the lessons learned to date, I would say the big one is it's not a certified airplane, but you almost have to look at every ATA of the 25 and 33 requirements to get it to safe for flight level. So we are drawing the perimeter, I should say, between the functions, whether it's a controls functions or a detection functions or protection function, they have to be implemented in a box. We have 3 boxes in our system, 3 main boxes: the engine control unit, the inverter for the electrical motor, and the BMS, the battery management system. And the key is to sort of define where the functions have to be, whether they're on the 25 or the 33 side. And I think that it will help the fact that we're doing the precedent of building that demonstrator, and we're doing it to make sure that it works and that it is cost effective and we can implement it easily. So we're creating a precedent there. The other area of challenge, we discussed that a little bit earlier, is the high voltage. So this thing is like, it's like you have a bunch of spark plugs and potential spark plugs in the system here. And the arcing detection and protection has been also very challenging. And thankfully, we're working with our friends at Collins. They are the state of the art into the understanding of that stuff. So very good that we're working with them. And then, so that's basically it in terms of the learnings. So now we're going full steam ahead. So the important is the techno bricks that we're developing. Again, they're enable a new design space for the airplane that could be very interesting in terms of productivity. So we're looking forward to the next steps and getting to flight. Thank you very much.
I'm sorry. Okay, our next presenter is GABRIELE TEOFILI. GABRIELE has spent 20 years in the aeronautical world, combining chief engineering and airworthiness competencies with technical and people leadership skills. Following his master's in aerospace engineering from the University of Rome, GABRIELE worked first in the traditional aerospace environment at the Leonardo helicopter and Airbus helicopter, carrying chief engineering and airworthiness responsibilities. Since 2012, GABRIELE joined the electrical aircraft development journey, first with Siemens and finally with Rolls-Royce. Over the last 10 years, he has led projects like hybrid electric multi-engine plane, city Airbus fully electric air taxi, taking them from scratch design to be airborne by his team. In 2021, GABRIELE founded the UAM program in Rolls-Royce Electrical and signed the first ever commercial contract for the newly born division with customer Vertical Aerospace. Since joining Zero Avia, Gabriele has led the team in delivering the world's first flight test program of the company's 600 kilowatt hydrogen electric engine aboard its Dornier 228 testbed aircraft, as well as progressing the design through its certification application. Gabriele.
Thank you, Gaudi. Good morning, everybody. Buongiorno. So we will start from where I left yesterday. If somebody of you was here yesterday, we went in a journey of describing what Zero Avia is doing, and we saw my slides starting from concept, the problem, the solution, and then seeing some rendering, and then seeing fly testing and real pictures. So today I will do a little bit of the opposite, because we want to speak about less or net of what we have done in Zero Avia. A couple of steps in the past. So 2020, Zero Avia is flying a Piper Malibu. First of all, 1 year before in California, with a full electric configuration, so having an electric motor stack and power converters in the nose, and then full battery configuration to verify that the aircraft was going to support operations with that propulsion system, and then moving to the UK, where we founded the second location of Zero Avia, and transforming the configuration from full electrical to half electric and half fuel cell. So 2020 we fly this aircraft where a fuel cell was used for the first time in a commercial aircraft configuration. And we always say this is the first time that a commercial aircraft flew with fuel cell and electric propulsion system. The aircraft flew in Cranfield during COVID in this period and performed 32 flights. And from that aircraft, we have built our understanding of how a fuel cell and hydrogen electric configuration can work, how it can be scaled, and which are the learnings from such a flight test campaign. I am not ashamed to say that there was an incident with this aircraft. I think everybody read in the internet. The aircraft landed a little bit too fast and too long on the runway because of a couple of learnings that we had from technical point of view and human factor point of view. From that incident, we came out with another type of company. So Zero Avia grew, became an organization with a lot of aerospace pedigree. We started building a setup of processes that resembled the design organization. We had a head of our worthiness, head of design organization, head of safety, head of quality, an accountable manager on site. We grew the pedigree, we grew the understanding of what aerospace means, thanks to a mistake. And I think this is one thing that always everybody try to hide. And nowadays, after the next aircraft flew, this was in 2023, again in the UK, in Campbell in this case, we took back the Piper Malibu. We placed it in the middle of the hangar. So if you enter in our hangar, there's a very small door that opens the door to a big environment. You will find it in front of you without wings as a memory of the past. Without that learning, we could not have flown something like this. This aircraft is a bigger aircraft with a certification basis that has to be supported, has to be verified. We flew, of course, both aircraft thanks to a permit to fly with the CAA in the UK. But having had that happening 3 years before allowed us not to be very, let's say, easy with the CAA. The CAA didn't make any discount to the next step for the certification, for the permit to fly. So what we have done in this case is, again, modifying one engine of the aircraft. The left-hand side engine is electric propulsion system. Inside the cabin, there is, again, half power given by batteries and half power given by fuel cell. And then we went into the verification of the risk and the safety cases for flying with this type of configuration of engines, verifying what's happening if the gas turbine will fail or if the electric propulsion will fail, and verifying if we were sure and confident enough to understand how to react in this case without improvising like it was done in the past with the Piper Malibu. So far, we have been right, and together with the CAA, we have demonstrated that the lesson from the previous step was important to learn, to implement, not only in the technology, I would say. Technology, actually, for the Dornier 228 was just as a double scale of the previous propulsion system with a lot of components off the shelf, not yet our own generation of parts, but with a lot of integration learning, integration capability, knowing how to use the power which is available inside the aircraft in a proper way in order to be safe in every single operation. So this takeoff, which was some months before the universal hydrogen aircraft, was a great year for fuel cell flights, where in 1 year, 2 biggest aircraft ever flown in the history of aviation with fuel cell made his debut. We have built on it. We have been flying 13 times. We have opened all the flight envelope we wanted to learn. We have studied the configuration and the components on the test. We have used them all in the selection of parts and selection of architecture for the next generation that we want to bring to certification. I will come back on this in a couple of minutes. We have another picture that I showed yesterday. This is something important. So ZeroAvia believes in making step by step. I mentioned you the type of flight test demonstration that we were having, the Piper with full batteries but the real propulsion system, the Piper in the UK with half batteries and fuel cell, and the propulsion system, the Dornier with one engine, traditional one engine with double power from the fuel cell. The next step is going towards aircraft like this. When we go in this size, it's not about just making a demonstration and then getting a couple of pictures. It's about knowing what you do in that nacelle. The nacelle is big. And therefore, before modifying that nacelle, we started making a lot of ground testing with what we call the hypertruck. So the small truck you see on the bottom right of the picture is practically ground demonstrator. It's a gigantic prop from the Q400 with a very, very tiny electric motor behind it. And of course, the gearbox and all the rest of the technology you need to drive the engine, which is, of course, power electronics, and the fuel cell that we had installed on the truck. Why we do something like this? Because when you go to this level of prop loads, you need to verify that your engine works not only in a dyno, not only in a test rig, and you cannot fly so early such a big amount of load. So we know from the past that the scale of learning cannot be jumped. We cannot jump the gun, and we go step by step in that direction. Piper, Dornier, Q400 or ATR-72 size of aircraft in the future, learning by testing many different parts in many different test rigs. We have learned that having an aerospace pedigree, knowing what to do more than going to get some results, but knowing why we got those results is more important, documenting the information, than just demonstrating that we can fly. We have done it in the past, and for the configuration we selected so far for the certification, which is the 600 kilowatt, the first engine, we know that now it's time to know and to demonstrate why we have availability of information about how to certify an engine. We're speaking about lesson learned today, and all the ideas of fuel cell electric engine start from this simple diagram where there is a little bit of particle molecules of hydrogen and oxygen entering the fuel cell, being transformed magically into electricity and water vapor, and then distributed to the electrical propulsion system, converted from DC to AC, and then transformed again with a second point of magic inside the electric motor from electricity, voltage, and current into torque and speed, so shaft power to drive a prop. This configuration here is a very nice picture, but will never be certified. And it's not a way that brings us to the future. Why that? Because we have understood, of course, we knew it from the past, but you try to understand if you have technology in order to fly, but once you have the technology, you have to understand that you have to come back to the origin, come back to basics, understanding what is your aircraft application, which are your requirements coming from the aircraft, how do you cascade your requirements to the singular system and then components, how do you build an architecture that can bring you to deal with normal, traditional requirements for safety, reliability, performance, function, etc. So the picture you see here, despite it's a difficult translation from that architecture to this one, is a translation of the learning. The configuration we have today is not a singular fuel cell box, which has a singular two phases cable going to the inverter and distributing the power. We have an architecture that foresees the capability to lose every single point in the engine, and for engine I mean fuel cell towards the shaft flange from the prop, without having failing one part of the system without risking to lose power and not perform the mission. So we learned to go from one configuration full battery to 2 configuration battery and hybrid to 4 configuration battery and fuel cell to 4 channels configuration for the fuel cell in this case. Fuel cell are capable enough to perform all missions despite losing one of the 4 channels. System architecture sounds the very first step of the work. Actually, the final system architecture comes only after having analyzed all the flight test data we have received so far from our aircrafts. There are different solutions for certification, which are also big learning from the analysis of the aircraft application. This is a Cessna Caravan. We have seen it fly with Magni X, which was fantastic, and the Beechcraft before, which was inspirational for us. The question is, why did we select the Caravan? We selected the Caravan because it's a very tall aircraft, has a very nice nose, has a lot of space in the nose, and under this big landing gear, very tall landing gear, there is a nice space for tanks. Otherwise, if we place these type of tanks inside the cabin, we're going to lose the whole payload in terms of volume. And how do you approach the certification of the tanks, the installation of the tanks under the belly of the aircraft, thanks to collaboration? So another big learning of our journey so far was that ZeroAvia has made everything by itself. You know, it's a startup. We buy an aircraft, we buy a second aircraft. We bought actually 3 aircrafts. You can buy all the aircrafts you want, but if you don't know how the aircrafts look like, how can you enter inside the aircrafts? So collaborating with Textron, which is our partner, means having the drawings, having the documents, having the requirements, having the certification basis of, unfortunately, 35 years ago, and try to understand how to enter in that old configuration without influencing the type certificate of the aircraft, but only having a delta, which is the engine. It's a big delta, of course, but we cannot restart from the beginning. Otherwise, we will never get there to collect flight hours in timing and demonstrate confidence of the system. So working with partners, in this case, a big OEM like Textron, allows us to become more real, to speak the real language. When we speak about crashworthiness, and we told, what do you think about installing those tanks under the belly? Textron replied, I didn't care, there were no crashworthiness requirements 35 years ago. So let's study together with FAA and the CAA, in our case in the UK, which is going to be the configuration which is giving us the best capability to de-risk the application of new requirements to novel, the old requirements of crashworthiness to novel systems like fuel cell, hydrogen gaseous tanks in this case. Collaboration is not only with OEM, of course, top level. We started with Textron, which was a big step, but collaboration means also having the right partners around us. A partner for tanks, which is not our vertical integration technology for ZeroAvia, partner with fuel cell stacks like PowerTrains, which is also a journey that we have to perform together. It's not only us needing to learn an aerospace pedigree or to collect experience from the aerospace or to respect the basics like top-level system engineering and requirement demonstration of compliance. It's everybody who works in this environment who needs to follow the same step. Otherwise, we will not get to the journey. So from one point of view, as I mentioned, ZeroAvia decides to reduce the risk that the main development of components will not run at pace by integrating internally the core components of the engine, which is the fuel cell stack in both fuel cell system in both LTPM and HTPM. For the LTPM, of course, we have a collaboration with PowerTrains, who is delivering the stack, and ZeroAvia makes the whole fuel cell balance of plant and system integration. For the HTPM, we do everything in-house, from stack design to fuel cell system design. Power electronics is a big step. We have an inverter which is undergoing already environmental test and ready for demonstration of compliance. We have FAA already witnessing our test. Electric motor, who got inspiration from all the development of electrical propulsion all over the world. Also my previous experiences in colleagues that came in from Magni X. It's a big community, in particular Everett is a big community of propulsion and power electronics. We can't hide that we have to do it together, that we are not going to make a competition against each other. There is space for everybody, and there is need of having an ecosystem that works together. And of course, compressor. So we need the level of compressed air to be able to have an efficient fuel cell chemical reaction between hydrogen and oxygen that, again, requires a rotating machine. And if you know, if you are an aerospace engineer or you work in aviation, you know that rotating machine is carrying as a tidal. And we decided to integrate it internally and to have alternatives like electrical compressor as well for the first configuration where we want to go fast. We want to have a configuration to bring to the authority, which I want to describe as boring. And my engineer hates me when I tell this. I want a boring engine. It has to boringly bring you from A to B without you noticing that it's a fuel cell driven by hydrogen. It has to be very, very boring. Then you have a good entertainment in the aircraft. And that's why we're selecting solutions which are available, which are internally developed. We know which requirements have to be complied in order to have that type of engine. We're not trying to find solutions with 20 or 30 suppliers for the main parts. Of course, we need collaborations with people like Textron, aircraft level, people like, in this case, Power Cell, Fuel Cell Stack, because we cannot do everything ourselves, and a number of other suppliers and partners. So the point I wanted to do in terms of lesson learned is not only having performance and functions demonstrated in flight or on ground like with our Hypertruck, is knowing why you got these results and also having documented them. So if you need to make a change, you have a change against the real baseline. Otherwise, we lose time. We have to come back from the beginning every single time. The second point of the lesson learned is not to forget the basics. We have to work via system engineering definition. We start from a system architecture. We start from an application, which is my aircraft. I need to know where is my engine going, and then we derive requirements and we cascade requirements down. A lot of traditional way of working with the speed and the pace, which is driven by internal selection of technology in the vertical integration, where we don't have to wait for others, we place our speed. And the third point I wanted to mention is partnership. That's all for lesson learned today. Thank you.
Awesome. Okay, so our next presenter is Susan Ying. She is the Senior Vice President of Global Partnerships for Ampere. She is also a Director and Board Member for the Lindbergh Foundation and the immediate past President of the ICAS, serving on the Executive Committee. Dr. Ying has devoted over 38 years to the aerospace industry with experience at NASA, Boeing, and most recently at the Commercial Aircraft Corporation of China as the Chief Integration Officer. Demonstrating success both as an individual and a team, Dr. Ying has been the recipient of many honors, including the People's Republic of China Friendship Award, the American Engineer of the Year Award, Asian American Engineer of the Year Award, Boeing Professional Excellence Award from the CTO and NASA Group Achievement Awards, as well as the AIAA Applied Aerodynamics Best Paper Award and the Professional Achievement Award for Women of Color. Dr. Ying is also recognized as a Fellow of the AIAA and the Fellow of the Royal Aeronautics Society. With a deep passion for flight, Dr. Ying holds a commercial pilot's license as well as an FAA-certified flight instructor. She received her PhD and master's degrees in aeronautics and astronautics from Stanford University and a BS in Mechanical Aerospace Engineering from Cornell University. Susan?
Thank you, Gaudi, for such an extensive introduction. And thank you for having me and Ampere here represented. I only have 3 charts because that's what Gaudi requested. So I'll just be brief here. Ampere is a small startup that's home-based in Los Angeles, California. And it was established in 2016, literally in the garage of one of the co-founders, Corey's father's home. And so you could imagine 3 young men working in the garage in the hot summer day in Southern California. That was in Temecula, actually, the wine country. But soon after that, actually, we moved into, I'm employee number 5 now. And soon after that, we moved into LACI, that's LA's Clean Energy Incubator. And then we were hatched. So we moved into Hawthorne Airport, where we had our very first flight, and you can see that for 2019 there. We flew, I think, in May 18th of 2019. And that was a really incredible moment for just a small team of less than 20 people. And so Ampere's vision is to electrify aviation. And in so doing, we start up with a electric propulsion system with a battery, of course. And then we wanted to first start with retrofit and gradually move into clean sheet designs that includes clean sheet airframe as well, because we very rapidly recognize the certification challenge, not just with the systems itself, but even the airframe, especially if you have any new elements of the airframe. So we started with the system, the propulsion system. And in so doing, we have had lots and lots of lessons learned in not just the flight tests, but also on the ground side. So in this journey, actually, we have come a long ways, thanks to the programs from NASA, as well as from the U.S. Air Force, and also the UKRI Future Flight Challenge program, where I think we even have a teammate from ZeroAvia for, I think, 2020 to 2021. That was really very exciting because being the first out there to flight test, and also flight tests under the FAA market survey experimental category. For some of you who might not know, why do we need to do that is, imagine on the ground when we have the automotive, all the new cars, when they come into service. Before that, you got to drive hundreds of thousands of miles on the road just to prove that you can operate under any circumstances, right? And so this is kind of like, instead of rubber meets the road, it's the wings meet the sky. And so in so doing, we really found out lots of very interesting situations, particularly, with the flight test. It really helped to uncover a lot of things that you don't discover in, for example, in the ground test or in the Copperbird, we call it, and also in the component test. So integration is very important. I was doing the integration role for the larger airplane back in Comac. In China. And it's quite a different thing because in this case, the atmospheric condition, the operational conditions, and so on, and of course, there's the regulations and everything that all come into play. And so we have done the flight tests, as I mentioned, starting in the US. So we flew in Hawaii under a program in Hawaii for the island of Maui. And soon after that, we went to the UK for testing in Scotland, in the Orkney Island, as well as down south in the Exeter, Cornwall, the English country area. And so all of those were pretty much short hops. And you would think that, short hops will be easy because there's not a whole lot of range challenge or anything. But actually, for the operational aspect, like from Logan Air and so on, the short hops are really fast. I mean, you're going from island to island, like no more than 10 minutes, including the offload of the passenger and cargo, and then loading again the new passenger and cargo. And so the whole thing for the loading, unloading is no more than 5 minutes. And so you don't have time to sit on the ground and do the charging. And so we learned a lot of the logistics aspect in terms of the island hopping, as well as operating in the different airports, because in this case, a lot of the operating procedures for safety, for example, for fire rescue and so on, will be challenged because the fire rescue for the lithium-ion fires will be a little bit different than when you have the Jet A or the avgas fires. So that's in terms of the earlier flights. And one of the lessons I think Pablo sitting in the audience we had was also in terms of our battery performance, because the very first battery that Ampere had was for the prototype testing was actually built by Ampere. Not the cells, of course. We put the modules together in the pack. And of course, the batteries, two things, of course, you have to do the cooling and everything, but you also have to assess all the data that come from the cells and the modules. And so the modules were all fine, except one of the modules always gave us kind of a different data than the other modules. And so we were looking all over because physically there was not really a whole lot of differences. So we kept looking into the software. Well, it turns out it wasn't the software, and it wasn't the hardware. But as we were kind of amateurs trying to put the pack together. And it turns out it was a little spider with a spider web in there. Somehow, maybe the spider was fried in the process, but somehow the spider web made a difference in the data transmission or something. So, well, anyway, we have decided to use the battery supplier partner afterwards rather than trying to do everything ourselves. So let me just quickly go to some of the highlights of these programs. And so in terms of our flight tests, we actually have 3 experimental aircraft to date. And as you saw in the previous chart, that we have made some world records. And so I'll go over these highlights. So far we've had 100% dispatch reliability. And so on the top left corner, you will see our flight to Alaska. And so that's an interesting flight with lots of learnings, particularly, well, I just mentioned some of the logistics aspects for flying in the UK and flying in Hawaii. But also we experienced that particularly in going through these places to Alaska. And also before that, we also went to Oshkosh. So prior to this, the Oshkosh flight was the longest distance of 1,100 miles, and Alaska was like 1,375 miles. And so in doing so, of course, we had to worry about the charging aspect because our architectures were mainly in independent parallel. Other than the very last airplane that's integrated parallel. So we have an independent parallel. We do have to charge the battery. And so trying to arrange charging the battery, even though the battery doesn't hold as much as a fully electric airplane, we still have to figure out where to do the charging, because if you try to charge, stop in a place, try to charge at 20 to 30 amps, that's very, very slow. You have to be there overnight or something. And so we have to plan ahead of time and arrange to have the charger and also the charging facility. And also another thing about flying up there, even though it's not strictly for IFR testing in this case, but still we had to go through a lot of moisture. And so this aspect of having to really look into the moisture or moisture inspection into our system, that's kind of a big deal. We have partnership with the KLM maintenance groups. And so we're writing also helping to write the maintenance procedures, but this fact of looking for the moisture in the systems is quite important. So that's an interesting case learned. But I also want to emphasize, it's interesting that with experimental aircraft, we flew to the EAA, which is the Oshkosh Experimental Association. So that's the annual flying with the 100,000 airplanes. And so you would think that there will be some charging capability over there. Turns out that we flew 1,100 miles, tried to charge over there, and they couldn't find a place that you could have the higher amperage for charging, or even 220 volts charging. And so we ended up using a diesel charger truck for charging. So all those charges saved for Oshkosh. So that's the top left. Bottom left, that's a proof of our endurance. So in this case, the endurance, we just flew over the Camarillo. That's where we do our flight tests. It's just south of Santa Barbara, north of Santa Monica. And so over here, we just flew around. In fact, Elliot flew around in circles around the area. And why do we do that? Because we really want to validate physically that we can achieve what we have designed, the battery in the system, such that we can have the battery only do the power peak, or the electric propulsion only do the power peak aspect, rather than for the entire propulsion requirements. And so that's proved. And upper right, you will see a picture of Elliot, our test pilot, flying our 337, which is an experimental aircraft, where we swapped out the rear engine to be the electric propulsion powertrain, and also actually in this one, the batteries are just in the back seat. And so the idea is that this is an ARPA-E program, where we do the testing of some of the new technologies or component technologies. And so the particular program that was supported there was a UC Berkeley power electronics. In this case, is called the flight capacitor of multi-level. It's a high voltage 800 volts DC to DC converter. And so the idea is that with such a high voltage, it's able to regulate that for supplying into the system, such that the system can get a really optimized performance. And so we accomplished the goal, but the idea is, like Gabrielle was emphasizing there, we need the partnership. In this case, some of the universities have the most current, or some of the really competitive technologies that are ready to be advanced to the next level. And so we work with the universities together. And so any of you, if you have some really great technologies you would like to fly on this platform, we'd be more than happy to collaborate with you. And also there are these test programs such as ARPA-E that could help to do that. And last one on the lower right-hand side is you can see this is pouring into the wing, the SAF, that's Sustainable Aviation Fuel. As you know, this is a hybrid airplane, and so we wanted to make sure that with this hybrid, we can also support the SAF, such that combination of the SAF and the electric propulsion, we can have up to almost 100% of the efficiency or decarbonized flight. And so the learning there is that with the SAF, we could totally support this flight without any impact to the performance and without impact to the systems. However, to the real proof is that we really have to fly this for many hours and then do a tear down of the engine to inspect that the real physical aspect of the engine, there's no impact, there's no tear and wear, that sort of thing. So advancing to the last chart. These hybrid electric airplanes will be able to scale, and will be able to scale much faster than if you just start with a clean sheet aircraft design. And in so doing, the scalable power, we can address that in many different test platforms. And while even though the first commercial product that we roll out is the Eco Caravan, and the Eco Caravan, in fact, we also test we also wrote a proposal to test in the central, in the Caribbean islands, and so with the different operating conditions and also with different requirements. Another thing is that we are right now in the certification phase, and so our certification plan has been approved by the FAA. So that's really good news for us because we have put in the application, I think, for a little more than a year. And another thing is that we are right now trying to certify, thanks to Magniacs, who have paved the way in terms of all-electric special condition. And so we have the all-electric part, but also we need to have the integrated parallel architecture certified. And so that's in work. Let me see. While while standing here, I'd like to do a little bit commercial for an upcoming session. I think it's on Thursday, right? Herb and Vince will be chairing this session. We'll talk about the certification aspect, some challenges and opportunities. And yes, and so with that, I think I'll conclude that it's been quite a learning experience, especially for me, because I come really from the big airplane background with Boeing for 20 years. My last job at Boeing was director for research and technologies. And so I've learned a lot in terms of not just the technologies aspect, but really the rubber meets the road, or the wings meet the sky. There's really a lot there, especially a lot for the technologies going into these new platforms and really decarbonize the aviation. So thank you, and I look forward to your questions.
Okay. Our next presenter is Miss ERIKA HOLTZ. ERIKA is a part of the aviation community since 2003 as an EIT, engineer in training. Okay. I'm sorry. So ERIKA has been involved in the aviation community all of her life, beginning with her professional career in 2003 as an engineer in training. In 2007, ERIKA completed her professional engineering status with the APEGBC and achieved her delegation status in 2010 as a structural delegate under the Design Approval Representative Program with Transport Canada. ERIKA has over 20 years of experience with modifications to general aircraft and over 15 years spent managing quality systems. Currently, ERIKA is the project manager and lead engineer for the Harbor Air electrification of the de Havilland to Beaver project, and was chosen last year as the one of the 8 women of Inspire by Elevate Aviation. ERIKA?
Good morning. Thanks for sticking around all the way to the end. I know it's been a very long session so far. So I'm going to give you a slightly different perspective. Harbor Air is an end user of the product as well as aircraft integration. And so my perspective is more about how we are actually using the aircraft in our operational environment and the lessons learned from that. But to start, just to give you some context, so Harbor Air is the largest seaplane operator in the Americas. We operate 45 aircraft, 12 destinations, and fly about 400,000 passengers per year. So I know they say that the small aircraft don't have a huge impact, but I think there are use cases where we are making an impact on regional transportation. The reason that the fully electric aircraft can actually work for us right now is because of this network that you see. Most of our flights, the average is 30 minutes. We don't typically fly more than 1,000 feet altitude for most of them. And so our energy requirements are actually really quite low. We also have all the infrastructure already in place for these aircraft. We have the aircraft, we have the people, we have the bases. All we need to do is change the propulsion to fully electric. So this was our choice, was to use our DHC-2 de Havilland Beaver. The baseline aircraft is 5,600 pounds gross weight, single pilot, 6 passenger. It had a 450 horsepower Pratt & Whitney R985 on it. And our entire design philosophy was the path of least resistance. Change the least you need to. It makes it easier on the technology, it makes it easier on the adoption, and it makes it easier on the regulator. The fewer elephants and the smaller they are to eat, the much easier this is going to be to get this into market. And that's what we want to do, is we want to be a gateway for early adoption of fully electric technologies, because we believe it'll be easier to certify those first, then move into the hybrid category and scale up to the larger aircraft and more complex systems. So we installed the Magni 500. I'm not going to talk a lot about that because I think David already did a very good job with that. He's incorporated most of our lessons learned on the engine side. I think the big takeaway from that, I think he repeated it a couple of times, don't look at your component in isolation. You need to look at it as part of the entire aircraft system. if you're only optimizing for your component, i.e. a battery module, you're optimizing for your weight, I might have to add 100 pounds of weight at the aircraft level to deal with whatever you're passing down my way. So we need to work on this collaboratively, and you need to look at how your component is going to be used in the aircraft application. So in addition to the Magni 500, there's a 150 kilowatt hour battery pack, approximately a 4-blade propeller. This was very important because for us, it's not just about removing GHG emissions, it's also about noise emissions. We operate in a very urban environment. We like to call ourselves one of the original urban air mobility places. We've been operating for 40 years in Vancouver. There are a lot of sensitive areas. Noise is an incredible issue for us, so that was one of our big balances. To date, we've performed, I think we just performed flight number 93, flying in and out of downtown Vancouver for the Everything Electric show. And we've been looking at all the different phases of flights, takeoff, climb, cruise, and noise, exploring cooling, LOPC, operational behavior. The cool thing about working so closely with our engine provider is that we have that feedback loop. They tell us, oh, we want you to investigate LOPC. I go investigate it on the aircraft. I feed back him some data. He goes back to the regulator and says, well, this is what we think is going to happen when we actually install this engine in this particular application. It was also important for us to look into operational behavior to see how this aircraft was going to perform within our network. So aside from the aircraft technologies and the improvements that we got on the aircraft, it was also understanding how this aircraft was going to work in our network. Our biggest lesson learned, I think, really had to do with charging infrastructure, and we learned something new this year. Again, also going to Oshkosh was one of them, but lack of power at scheduled points. The charging infrastructure is a real problem, and actually we made it worse this year. So last year we were running a battery system that was about 537 volts was the max voltage on that system. For a variety of reasons, we had to take that battery pack out and replace it with a new system that just got operational earlier this year, and it's an 801 volt system. We discovered when we were trying to go to Oshkosh that nobody is making a charger that's 220 volt single phase or lower. All the chargers that are out there are built primarily for electric vehicles. Electric vehicles generally seem to be more at 500 volts plus or minus. So these chargers tap out at about 750 volts. I had an engineer work for an entire week trying to source a charger that could take us to 801 volts on 220 volt single phase power or less, and he was unable to do so. So last year, we were able to fly our aircraft in our network to places like Salt Spring and Victoria, and this year I will not be able to because I do not have the voltage necessary to run our big charger. I don't have 480 volt 100 amp service at any of those locations, and I don't have a charger that can work on anything less. And I think this is a problem. I see a lot of people are throwing that 800 volt number out there, and I don't think that our charging infrastructure is able to support that yet. It's a significant issue, and I think that I am seeing, I think Polestar now has a car out that's 800 volt. Maybe the electric vehicle market will move into that, which will drive the charging manufacturers to make charges that'll work. Otherwise, we're going to be building these aircraft that we're only going to be able to charge in very specific locations, not everywhere we want them to go. Approach to thermal management, I think, is one big one that we need to hit as well. It's not just about the total temperature of the batteries, it's also temperature differentials. We might be seeing this a little bit more because we're a retrofit. So I have different zones. There are some batteries forward of the firewall, some batteries in the belly of the aircraft, and some batteries inside the fuselage. So we get temperature differentials during the flight. We also, of course, have temperature rise because when you discharge, during flight, you add heat, and when you charge, you're adding heat. In flight, we cannot afford to have any active cooling. It's passive cooling only. And I know the manufacturers of the batteries, that's all we're looking at right now is passive cooling. And it gets us a flight. But it only gets us one flight. As an operator, I will take this aircraft and operate in this exact location, and I will want to fly it 12 times in a day, running tours, so people can say that they flew in a fully electric Beaver in downtown Vancouver. And currently, I'm not going to be able to do that unless I have active ground conditioning when I plug in for the charge. So one of the things we're really looking into this year is the ground conditioning system. Our idea is that when the aircraft comes in for charge, you come in, plug in the charger, you also plug into a port to flood the battery system. Air cooling is not going to be enough. The environment is a lot more influential on the battery than I think that many people predicted. When we took this thing downtown and parked it on the water and we were charging it, we were getting an 8-degree temperature differential in the single battery module that was in the belly of the aircraft between a cell that was on the bottom of the module and a cell that was on the top of the module. The heat sink from the ocean was so influential on the batteries that it actually caused such a differential in our battery pack, the charging kept stopping, because inside the cabin was more than a 15-degree temperature differential then to the modules that were in the bottom. And so I don't know that everybody is really taking into consideration how impactful the environment is going to be. Even if you're a clean sheet design and you manage to put your batteries in a single pack, the batteries on the outside of the pack versus the batteries in the inside of the pack are going to be at different temperatures. And the longer that you run it, the longer you charge and discharge and cycle it, the worse that's going to get unless you moderate it. So I think ground conditioning is going to be mandatory for your end users. The other thing we get to do with this aircraft is kind of fun, is this is our technical demonstrator. There's absolutely nothing in this aircraft that's going to certification except the propeller, and if Ben has his way, I think he wants to get rid of the propeller too, so we'll see. But I like the propeller, it's fantastic. This propeller, the efficiency gain was so great. I think this is one thing that's interesting from a retrofit perspective, is some of these older aircraft are so inefficiently created. They got the big radials on the front, these old propellers. We really benefited from a performance improvement that was somewhat unexpected, which is what changed this from a technical demonstrator and is taking us down the path to commercialization, primarily due to this one number change, which is that the original Beaver at 5,600 pounds piston aircraft required 62% of maximum power in order to maintain level flight. With all these changes on this aircraft, we were able to reduce that down to 41% power for level flight, and you use that cruise setting to calculate your reserve. That is incredibly impactful. So if you're looking for an aircraft to retrofit, look for one that is incredibly dirty in terms of drag, and you will be able to make it a lot better. So onto the architecture stuff. So things we got to play with this one had to do with the strings. Our first set of batteries, we were 3 strings bussed together to feed the engine. We got to test that out. What we're running right now is a string per inverter, trying to figure out which is the best architecture. I cannot advise you on that yet. We're still exploring. I can tell you that one interesting thing we had was a big argument at the beginning about what pilots need to see and don't need to see. And then we flew the bus together system one time. The pilot reported that his energy drained a lot faster than he expected. We took it back to base, inspected, and one of the cables for the high voltage system had come loose. And there was no CAS messaging for the pilot because nobody was monitoring currents, because that was one of the arguments we had, was whether or not the pilot needed to know about the currents, because he had voltage, he had power. What did he need currents for? Well, in that system, he needed to know currents. With the not bus together system, when we have a battery string per inverter, we won't have that problem. It'll be very noticeable when you lose a battery because you're also going to lose power. So our system safety analysis division is looking into that, still trying to figure out which is the best way to go. And a lot of that has to do with the fact that we don't have all the reliability numbers that we actually need for some of the components. We have to assume worst case scenario, which may drive us back to the bus system just because of that. I think one other important lesson on the architecture that we learned had to do with the modules themselves and string balancing logic. We lost our first set of batteries because of cell balancing. That was the fundamental problem. We had a parasitic draw, we couldn't find it, so we let the system balance. But what we didn't know was there was a piece of software in there that when you had the software connected and were actively running balancing, the software would actually engage balancers on cells that didn't need to engage them. Every 15 minutes, it would engage it. I don't know why the software did that. Nobody told us the software was going to do that. I think the big lesson learned there for us was that battery suppliers who don't come from an aviation background don't know what the end user needs, and the end user doesn't know the questions to ask. So it's very important, again, circling back to that, work very closely with your integrators and your suppliers so that everybody understands the ramifications of everything that you do with the system. I think the last piece I have to leave you with is also not, again with everything looks like a nail when you're a hammer, not everything needs to be solved with software. Mechanical systems have worked for many years, and again, back to that path of least resistance, sometimes mechanical systems can be left alone while you focus on the novel technology areas that actually need to be changed. I think you already covered this a little bit under safety aspects. There is something, it is very different. I think our biggest one for us is actually operation on water. We're working with the NRC in Canada to actually look at submersion. Even though EVs do submersion, it's all company testing. There is no industry standard for us to meet. So it's something we're working on the NRC with so that we could at least come up with some kind of design practice or standard that we could meet for submersion. Safety, I think the automobile rescue charts of ISO 17840 should be something considered by our industry. I think that would be a very good idea. And of course, training. And I think that's it for me.
So not quite as much time as I had hoped for questions, but I would like to open the floor for questions. We have two young ladies that will help us ask the questions. So I see a hand up, Dahlia. Oh, wait. You got to wait for the microphone. And the microphones are right there at the table, so.
Thank you very much, Gaudi. Hi, my name's Dahlia Pham, and I work at NASA Ames. And actually, something that I was thinking about the electrified space is that it really is a partnership between, industry and also agencies to work on sustainable aviation. And I know that from my experience, I used to work under Susan, and then now I meet with Dave like twice a month, and I work under Gaudi. And there was a question that Lee Noble asked me when he visited Ames that I thought was really good. It was, what benefit do you get from working with industry partners? So I want to turn that question to this panel and ask, what benefits do you have as industry partners working with NASA, and how can we improve those areas as well, and any lessons learned? So this is kind of a question to everyone in the panel.
And if you do not work with NASA currently, your partnerships with other government agencies in your home countries.
Yes.
Well, our very first collaborator was with NASA, and so it was to prove the concept of a sort of a ducted fan. In fact, that was inspired by a long time ago a NASA paper that actually for reducing noise for using the ducted fan. So from a technology perspective, the know-how, the people, I think it was really great start. But also we have another partner, ARPA-E, which I'd like to mention, is that, for example, right now we're on this scale-up program. And as I mentioned in my last chart, the hybrid electric technologies is ready for scale-up. And that's very important because, for example, for many of the startups, we know how to make small airplanes, but growing to bigger airplanes is a lot more complexity, and there's a lot of areas that require expertise. And for a company with 30, 40, or 100 people, you might not get that expertise and also experiences from the industry. And so that partnership with ARPA-E and with other industries is has been really helpful. One last thing I want to add is I think Gabrielle, you mentioned, and maybe the others also mentioned, is in terms of the standards, the industry standards, which are important to put into the certification aspect. So, for example, why the certification of these radically different technologies and novel technologies are so hard to certify? Well, because the standards or new rules don't exist yet. And how do those get formed? Well, the industry sit together at the same table and discuss, debate on the various standards that should be for the future product. And so that's a process, that's a democratic process. And so it's a bit slow because everybody needs to participate, everybody has a voice, not noise. And so I think that's been really beneficial, having the industry as well as the government partners.
I think you mentioned almost everything. I would like to give an example of my last 20 years, were 10 years in certification and development. and then 10 years in the electrification of aviation. So one problem that I faced is the lack of customer in the electrification of aviation. We are seeking for a customer like crazy. I want to have somebody who is challenging me. Why? Because we have development of technology in-house, development of certification baseline in-house, partners with industry, yes, civil aviation, yes, but nobody who is challenging you and asking you why your design works fine, when are you going to deliver it to me, with this function, with this performance, with this level of safety. So without having an ecosystem of people, even if it's only a partnership, which is confirming with each other if every single part of the architecture or requirements can be achieved, we will be walking alone in a sort of confirmation bias, internal. We think we are the best because everything works according to our expectation. But when you are confronted with a customer, and this comes from normal product development, it's a total different story. You have to achieve milestones in time, you have to achieve performance, you have to make compromises, you have to negotiate if your performance are lower. And this cannot be done in our industry today, in the electrification of aviation, because we cannot compromise with the requirements, because the requirements are still all airworthiness requirements. So I welcome every single part of collaboration with OEM, for example, or operators. Operators are also very demanding because it will remove the confirmation bias and discover the real problem we may still have in the full certification approach.
So, I can give a quick example. So for our system, we needed a charger that could go both ways up to 1200 volts, so that doesn't exist. So we worked with the NRC lab in Ottawa to help us out, and we made our own custom charger system. So that's an example of collaboration. So on top of the governments that are helping financially, the high-risk development of the high-risk system, we're getting help from the expert as well from the lab. So we have to collaborate. There's no other way. Thank you.
Fantastic question. I think, firstly, looking at sort of agencies, in general, I mean, we're very fortunate to have, the EPFT program with NASA, good relationships with a lot of the regulatory authorities around the world, the FAA and Transport Canada, et cetera, from the interactions that we've had. And, the level of support has been fantastic in both of those. I think, to pick on one specific example of many with the NASA collaboration, I think it certainly is a stepping up. On our side, in terms of, you're dealing with the people that wrote the book, literally, on systems engineering. I think one of the best elements of this has been, from a collaborative point of view, a lot of the development lifecycle work, in aerospace. We're used to DO178C, DO254 processes. We're implementing those at MagniX. We've been through SOI 1. We're entering SOI 2 for a bunch of the aspects that are underway, these sort of key milestones on the road to certification. And NASA has its own NPRs related to software development, right? So you're working cross-collaboratively in those two things. We found really this project is something of a babblefish for translating across between the different authorities, different agencies around, and information exchange and sharing, so that there is this common language, this common framework that's going to lead to sort of a more robust understanding on how we execute development life cycles, in software and complex hardware, systems engineering across the world. It sounds like a minor thing, but it's really critical when you are operating in a highly regulated, requirements-driven environment.
Thank you, David. ERIKA, anything else to share?
For us, we're working with both Transport Canada and the National Research Council of Canada. And Transport Canada has been excellent at sharing what they're learning with the CMT, which is the collaboration between the FAA, EASA, ANAC, and Transport Canada to make sure we're harmonized on the path to certification. The NRC was really exciting because the submersion test that I talked about, their standard we want to develop, they actually had us look at an analysis of the potential failure, what happens if we are submerged from a very different perspective, because we don't have the reliability numbers. Typically, it's quite easy. You know exactly what, somebody says, okay, this is good to 10 to the -7, and you add that up and carry on, do your fault tree. We can't do that with some of our components, and we don't know how they're going to behave when they're submerged. And we don't want to just say, okay, you assume submersion and everybody's going to die. That's not the way we want to go with that either. So they had us look at a very different approach to how to do the submersion analysis to determine what is and what is not a true hazard. It led us down some very interesting paths. And the next step that they want to do is actually help us develop a submersion test and take it all the way through to actually testing some of the components, which allows us to do stuff that we wouldn't be able to do on our own. I have a team of 5 engineers. We're very small. We're capable of doing structural work primarily and some mechanical work. But when it comes to actually testing any of those types of components, it's not something we're willing to invest millions of dollars in creating our own lab. It gives us access to tools and people that we would not normally have access to.
All right. Thank you very much. Any other questions? Sir, right there.
Yes, hello, Vincent Foucard from Clean Aviation. Thank you for your inspiring presentations. My question is about the commercial exploitation of the battery-based hybrid electric technology. How do you see the possible products which could emerge from this technology in terms of capability, so capacity, range, considering the current limits of battery technologies and its future evolution in, let's say, 10 years from now, moving maybe from 200 to 500 watt-hours per kilogram?
Well, I can take a stab at it. So, like I mentioned, we're using the electrical power for to help the engine cycle. So we minimize the amount of energy that we use from the battery. In our case, in our architecture. So I see that, and the full discharge, most of the times you don't fully discharge the battery either, because you have to keep some for safety and maybe a go around potentially. That happens almost never. So in terms of cycle life, we're not that worried, and the size of the battery should be manageable as well. And to many applications, even it will be recharged in flight. So that's how we intend to manage it. So basically, we minimize the problem by minimizing the energy. And as the energy improves, then we could upgrade the system and use a bit more of electrical power. But fundamentally, it's an help to improve the engine cycle.
Okay.
I think for us, what we see is, if we can get to that kind of 500 watt-hour per kilogram, we're looking at aircraft, somewhere between the 9 and 19 seat could go fully electric. Anything 19 seat and above is probably going to have to be hybrid, which would pass it over to you.
Thank you, Erika. Yes, currently we already have a 9-passenger hybrid electric first commercial product to be out by 2026 for the LA World Soccer football. And so I think it's not very far. In fact, I just came back from China last week, and there, 500 watt-hour per kilogram pack level is already being addressed seriously by COMAC and its partners. And so I think the day that you will see fully electric or hybrid electric product is already here. And I'm sure my colleagues here would also agree with you with the hybrid. As you can see, the endurance is tremendous, like orders of magnitude over the fully electric. And also from a logistics perspective, I think more of a challenge right now is discovering things such as chargers and infrastructures. Those have to be ready. So even if you have 1,000 watt-hour per kilogram, well, you're gonna have to draw clean energy, right? Because if you just have the grid energy, which may or may not be green, so you're just shifting the problem. So the airports have to be ready, the chargers and all the infrastructure, and the whole ecosystem has to be ready. So that's more of a challenge than just the airplane alone.
Okay, thank you very much. One last question before I ask each of my panel members to say a few closing words. I'll go to Mike. It's Mike, right up there.
Hi again, my name is Mike Walls. I work for the FAA. In the certification aspects that you guys talk about, Magnex, we know we have 33 special conditions that are out there for you, but those are across the board, and we use those as like a baseline to move forward. My question to the panel is, with those in line plus the 33 that we actually use, there's 33 special conditions plus in part 33, we've gone through this. We've spent a lot of time harmonizing with EASO on a lot of this. I would like to know which aspect that you guys find the most challenging?
I can start from my side. Yes, magnetic special condition is an inspiration for propulsion system, of course. The challenge we see from propulsion system point of view is that developing one engine that fits all is not really possible without the definition of the application, despite the concept of special condition. And there we have to enter into definition of interface, for example, of the propulsion system, which may fit different configurations. It's a very advanced discussion with the FAA because of the work that was done in the past 5 years. In the EASA world, in Europe, with the CAA and the collaboration we have with EASA, there is a different approach with the Special Condition 19, which requires a deeper discussion, a deeper suggestion from our side how to translate it into different applications. The most challenging aspect I find myself is the lack of standardization for utilization of hydrogen, lack of standardization for development of hydrogen-related parts, contact with hydrogen, and of course, bigger problem that will come from integration, like I was mentioning yesterday. How do we deal with the positioning of new system into aircraft in traditional sections of the aircraft of new components which are just novel for a civil aviation. So the level of education that we have done inside ourselves in the organization has to be shared, the learning has to be shared before even approaching the definition of a certification basis. It's a journey that requires time in the beginning before being able to present a certification basis which has a robustness and a confidence. And I think this is for me the biggest point.
Okay. And go ahead.
Yeah, thanks, Mike, for that question. I think for Ampere particularly, we have come to an agreement with the FAA in terms of our cert basis, which uses the special condition as well as the other aspect of the integrated combustion engine and the electric. And so that's the part I think will be the new aspect, particularly with the integration, because when we do the test, the flight test, our proposal is very unique in terms of flying the combustion part first and then adding on. So it's really a mildly hybrid kind of situation. So we appreciate the fact that it's been approved, and so now we're moving on to the next phase.
Well, I don't have as much of a problem with the Part 33 certification because he has to do that for me.
Yeah, I think going on a panel and saying what's the greatest challenge you have with the certification side is probably it's quite a topic. I think I would say firstly we're very appreciative of the support we have and the conversations we're having with the regulator on the special conditions as they were developed and as they were issued, in 2021. I think I'd like to answer the question by talking to one of the success stories in the discussion. Certainly, from my perspective, one phrase that kept me up at night for a decent period of time was, I believe, it reads something like, shall be essentially single fault tolerant as determined by the regulator for electrical, electronic, and electrically detectable faults with respect to LOPC. And so that is verbiage that comes from other parts of the regulation. It's very standardized, and so one understands why it entered into the LOPC conversation. When you look at the scope of what that defines in a conventional system versus a fully electric system, that's a lot of scope, right? That includes aspects of the windings, it includes the cables, it includes each of these things. There was much debate back and forth about what that meant in the LOPC. Now, what was great about that, and I think what is the essence of the certification journey at the moment, was the ability, for ourselves with our partners in Harbour Air to advance the nature of that discussion, both with the regulator and in the standards committees through a lot of the work that's ongoing, good work that's ongoing. And again, I just second Susan's point about Herb and Vince's panel tomorrow as well, on Thursday rather. But what that allowed us to do was from our own testing and from our testing in partnership at the aircraft level with Harbour Air, was to actually bring some data to the table into those discussions, and I think really create a framework, or help to create a framework, help to produce a conversation in the industry that really led to, I think, a good understanding of what that meant and the paths forward through that thing. And I think if we continue to do that for each of the essential elements that are going to come out as part of the certification, you know, obviously we have dialogue with the regulator through white papers on areas in the performance-based language where means methods of compliance do need to be slightly more, we need to propose something slightly more concrete from that perspective. As long as that continues, I think we're in good stead for, you know, a bunch of the topics, you know, vibration surveys, operational surveys, endurance, durability, IMI, all of the things that essentially form part of a traditional engine project, but now referenced in the electric space.
Jean?
Yeah, we're going to watch what's happening with the full electric systems, but fundamentally for us, we'll manage it with the size and manage the LOPC with how much electric augmentation we use in the system. And we start small and we grow as we gain confidence in the system. I think that would be the pragmatic approach.
Okay. Susan?
Yeah, just one last comment here. I think it's a lot more than Part 33, because for Part 23, particularly with the battery pack system integration, I think that's where a lot of the challenges, you know, the thermal runaway and some of those tests there right now are in heavy debates, and we're looking forward to getting that part of our CERT plan approved and move on.
Great. So so bear with me, just 5 more minutes. I'd like to give the panel members each a minute to give a key takeaway for our community.
I get to go first with that much notice. And the key takeaway, I think the key takeaway for me fundamentally is, you know, the technology has reached a point both on the propulsion side and on the energy storage side where we can start to attract very interesting and commercially viable missions as outworked with the conversation partnership we've had with Harbour Air. You know, the challenge now for us as an industry beyond the technology piece of the puzzle is the path to certification and entry into service, the focus on the data sets that are going to underpin the development of regulations where there are gaps and the showing of compliance against those regulations, you know, where they are currently in place. And I think if we address that in the next couple of years, I think initially through an all-electric type application and expanding out through hybrid, through hydrogen, each of these different elements, then there is a roadmap and a path to actually bringing this to commercial reality and entering into service, and then making a manifest difference on the charts and the emissions charts that we've seen presented throughout this.
Thank you.
Yeah. So something like airplanes today are really good. If you take just a snapshot of a turboprop airplane flying at the cruise point, you know, it's between 2 and 3 liters per 100 kilometer passenger, so airplanes are really good. So whatever you come up as a concept to change the game, you need to bring that number down. So just keep that in mind. Thermodynamics matters, and fundamentals need to be in the box. Thank you.
Thank you, Jean. Gabriele?
For me, it's participating to this type of panel is an evolution of this type of conferences and speeches, because we are not speaking about efficiency anymore. We're not speaking about architecture, 1 line, 2 line, 3 lines. We have use cases. Now we have confidence about the technology. We need to bring the technology to product development and certification, and we are all speaking about having a partnership, extending the ecosystem, becoming real. And it's a nice evolution to be seen in the last, I would say, 5 years, not too much. So I'm very confident that in the next 5 years we speak about flight hours of a type certified system.
Thank you. Susan?
Yeah, we're living in this very interesting times, particularly in our industry. It's called the third revolution right now, right? Because we've been in the evolution of the business for a long time. And so in this revolution, we need to move the whole chain, not just the industries, but also from the innovation, from the universities, all the way from R&D, and down to the certification. So how can we all move together faster so that we can beat this zero emission? Right? So that's my thing, just to really work fast, work together, and making this happen.
Okay. ERIKA?
I'll just circle back to what I said, and I think David said it earlier, is about the partnerships, the working together. If you're working on components down in TRL level 4, 5, and 6, you need to be talking to people like me who are working in the 7, 8, 9. We're trying to use your components. You need to be talking to us when you're developing the TRL 4, 5, 6, or it's not going to do what I want it to do as the end user.
Thank you so much. Let's give a great hand of applause to our panel members. Thank you for staying with us for all of this, and look forward to 2026 in Sydney.